Jake.
Everybody, we're going to get started. So I just wanted to say thanks to Detroit Radiant and Loren Cook and AbsolutAire and Aire and Airius for dedicating their staff to come here and do a live event when a lot of the folks are actually remote. But when I first sent out this invitation, I was like, well, I don't exactly know how they're going to respond. So we're, for example, the infrared company and the makeup air company, in some ways are competing on building strategy. But in other ways, like, well, I'm a little bit, for me, I'm scratching my own itch here. I want to talk about how things work together, not how they work independently. Should you have destratification fans in a system that has infrared heating that's heating the floor? Do you necessarily need to have a lot of ductwork in a building that's heating only? What's the best combination? And certainly one of the items that we're talking about today gets value engineered a lot, air curtains. So if you have a heated building that's properly pressurized, do air curtains actually make any sense? So we're going to explore all those different items today. It's going to be a long class. Well, your PE, you're going to get rewarded handsomely with 4 PDH credits. But I'm curious for myself, and usually that leads to good stuff. One of our core values here is about being driven to learn. And I know when I talk to contractors and consulting engineers that there's a lot of room between what we feel like they ought to know and what they actually know. So if you're one of the people here or one of the people out in the interwebs sitting in, or if you're watching this class later and it's recorded, good for you, because there's a lot of juice in the nuance. And so I think all this stuff is really interesting, and I've been doing it for a long time and it stays interesting. So wherever you're at, there's a lot more to learn, whether you're a KG Pro of 30 years or whether you're 3 months into your new job, there's always more to learn. So with that, we've got Joe Wortman, president of Detroit Radiant. He's going to kick us off for about the next 70 minutes. And then we're going to have a break. So buckle up. Here we go. Different format for Joe.
Yeah, right.
So here we go.
I found out just a few days ago it has to be on PowerPoint. I'm like, I don't do PowerPoint. so I put something together. But good morning. Thanks for having me out here. And Tom, thanks for the introduction. Looking forward to teaching you about infrared and maybe I'll dive a little bit into some of the macro items that affect our industry today. If you could advance the slide. Last night, I rolled into Wisconsin. I put that slide together. I come to Lake Geneva once a year I have another business in Wisconsin and Chicago and enjoy that. I've watched your Green Bay Packers destroy my lines for 50 years now. Although that's changing.
This year.
Yeah. My dad is a Marquette grad. So that's kind of cool. And I came in and have you noticed that your aviation museum at the airport when you come in? So last night I saw that. I took a picture of it. And in so many ways, I'm a pilot. So the whole aviation thing was pretty cool to see. I'm gonna look forward to stopping there today. But then the space shuttle itself, we teach a lot about infrared heaters from it. The bottom of the shuttle is coated black for the emissivity. Right, the ability to radiate the heat away. It had ceramic tiles on it, protect it from the heat. It had titanium wings. And you remember that particular shuttle, when it broke apart, was because the ceramic tile cracked. And so there's some parallels to what I do. But then also, I had a chance to spend a week on a ship a year and a half ago with a 5-time NASA astronaut. And he had 5 launches on the space shuttle. And hearing it from his eyes, knowing what happened on this particular mission, it was really kind of wow. So I had to show the picture because it was just staring at me last night when I landed. Next slide, please. So Detroit Radiant Products, we are a true manufacturer of infrared heating equipment based out of Warren, Michigan. Obviously roots to Detroit, but we're right on the border. And we were started in 1955. So it's family owned. My grandfather was one of the founders, and his roots before that was making artillery shells for the US military. He was from Germany. That really bothered him because the artillery shells were being used against his brother who was fighting for the Germans in World War II. After the war ended, he moved the tooling and the dies over to making copper toilet floats that, that you put in the back of a toilet. And it was very much a process of drawing steel where you take a flat piece of metal and you form it, right? And it's kind of an art. You need to have a certain skill set to do that in the tooling industry. And then we were making about 2 million floats per year, and then plastic came along. And at that point in time, 2 years later, there was no demand for copper toilet floats because plastic had taken over. So what do? Well, the infrared technology, have you heard of Schwenk? Perfection Schwenk, it's a competitor out of Germany. He was looking to license a company called American Infrared to manufacture heaters in America. So my grandfather came on, he was older by then, and they came up with the name reverberate. And if you think of the word reverberate, the explosion reverberated through the community, or the music in the auditorium reverberated against the walls. It's to bounce off of things. So they did a little play with reverberate. It's an infrared ray leaving a heater and hitting an object. In our case, at that time, it was a rod that we put in front of the emitter and would bounce back and make the surface itself hotter. And we'll get into this a little further, but Stefan Boltzmann law, it's temperature to the fourth power. The hotter the element, the more the infrared heat that goes out. So we came up with the name reverberate, and since 1955, we've been making that. Kind of cool to watch us on LinkedIn or Facebook. These are some of the pictures of our operations. Press brakes and plastic injection and automated paint machines. But just this week, we added our second fiber optic laser. And actually, it has an auto feeder that all night long you run off your iPhone, and 24 sheets of steel get cut every night, looking at it on the phone and controlling it. So we truly do manufacture. And I would encourage you, as we post our new equipment, to just kind of follow us on one of the social media things. Next slide, please. So this is what we do. And Tom, I thank you for this piece that I'm sharing about the different products we make. We make unit heaters, ceramic heaters, tubular heaters, a full line of electric heaters now, patio heaters, which was huge through COVID. And then we bought an LED lighting company, which is a little bit of a break from what we do because it's a different trade. But they don't build them like this anymore, except in Detroit. It was inspired by those posters in your hallway downstairs, and we hired your marketing group.
But did you really?
Came in and they made about 9 different things for us. So they're kind of, clever. How to fasten tubes together. We swedged it, but they managed to take a swedge fit tube and tied it together with a seatbelt, right? And so it was pretty clever what they did. So I kind of wanted to share this piece, but this goes in with every single heater we send out, just reminding people that we make different products. And a lot of people don't think of us for hot air heaters anymore, but we have a full building dedicated to that. Next slide, please. So a little bit about myself. Joe Wortman, President and CEO of Detroit Radio Products. A third generation. I'm the generation that's supposed to screw up the business, right? The first, the second builds it, the third breaks it. But so far, so good. So I've been at this now 31 years full-time out of school. And my background at Western was finance and aviation. So I left Western Michigan as a flight instructor, but also with a finance degree. But when you grow up in a family business, that's all you know. So I grew up around heaters, and I since went and got my master's, and kind of cover all aspects of small business. I have 4 girls, no boys. 2 of them are teenagers, and that is interesting. Somebody who grew up with all brothers, we just beat each other up. But the amount of tears with girls, it cracks me up. But that's been wonderful. I still teach people how to fly. I wish I could share it, maybe we can, but I've done some really neat adventure trips all over the world, which has been fun. But, day in, day out, this is what I do, heaters. Next slide, please. So this is the question that I struggle with, and I get asked often. I go to an engineering presentation and people say, I'm busy, got 15 minutes for you, sit down, how efficient are your heaters? And I'm sure any of you have gone in and called on a professional engineer, how efficient are your heaters, is a question that they often ask. And I sit there and think, that's a hard question to answer in 15 minutes. Because are they referring it to, are they a combustion engineer? My engineers want to look at efficiency different up in the lab. Okay, is it the end user who's worried about how much it's going to cost to operate? Is it somebody who's very, earth conscious and wants this to be super green with the emissions? The efficiency question is a tough one. And if I pull up this presentation right, I think by the end of it, I think I'll give perspective as to what efficiency means. And if we advance to the next slide, I think the government's trying to do the same thing. I looked through the years now, and we've had Energy Star. Remember you bought the thermostats or the pieces that are Energy Star compliant. And then do you remember when every building had to get LEED points? That's kind of phased out a little bit, but you'd have to show how infrared heaters contributed to LEED points. And then Aire is trying to come up with a standard for efficiency on how radiant efficient a heater is. The Europeans are pretty far ahead of us with regards to radiant efficiency, also combined with combustion efficiency. That's the EU regulation 426. And then we've got solar energy, windmill energy, compressed natural gas, and electricity, right? So I think in the past 3 months, I've had 5 reps call and say, you need to totally abandon what Detroit Radiant does, burning gas, and switch everything to electricity. And I remember 3 or 4 years ago, every single bus station in Atlanta, Chicago, all the major metropolitans were switching their fleets to natural gas. If you look through the years, the trends change. And right now, certainly electricity is a big one. And we are moving towards making electric heaters, but we also, are rooted with natural gas and gas products. So I want to talk a little bit about natural gas just before we start the presentation. Next slide, please. So I was at a thermal incident in Montana this weekend, and that is legal code for fire. There was a fire loss, and the lawyers don't like me saying that word. And as I sat right outside, it was Livingston, Montana, the entrance to Yellowstone National Park, trains went by me all weekend full of coal. As far as you could see, there was coal trains. And I'm sitting here thinking, aren't we trying to get away from coal? It was kind of ironic that the beauty of the mountains and all the Yellowstone has is just being pulled coal out of the ground. Is this going to China where they're opening 1 coal burning facility a week? I've been to China a lot. It's amazing how the air pollution is there. Or is this going to create electricity or warm a home? I don't know. But I was really intrigued by it. So I started doing a little research. Next slide, please. And this is energy consumption from 1950 up to 2020. And you can see that coal is declining, but it's still a big producer of total energy for the United States. Natural gas has remained somewhat constant, is actually a bigger piece than it used to be. Okay, then we have petroleum. And then you can see towards the top, we have nuclear energy, somewhat constant, and then renewables. So I thought that was interesting. The next slide talks about 2020 versus, the year 2000 versus 2021. And you can see right here, coal and gas have remained somewhat constant. As has nuclear, but if you look in terms of renewables, solar and wind power is starting to match the graph up towards the top. It's becoming a greater part of the energy creation in this country. But by far, coal and fossil fuels are the primary driver of what heats and how provides energy for this country. Next slide. If this is right, the World Energy Outlook for 2022, it'll say somewhere around the year 2030, renewables will pass gas. I'll believe it when I see it. But again, I start this because I've literally had 5 reps say you need to shift your business to electric, right? And I'm sitting here a little bit puzzled as to how long this trend right now, if you're seeing it in this room, are you seeing this?
I'm doing presentations on this subject regularly. And what people unfortunately don't understand is when you plug your computer into the wall. That's powered mostly by natural gas,
Yep.
somewhat by coal, a little bit by renewables.
Yep.
And so it's just a failure, and 2/3 of what's produced by those by coal and natural gas is lost in heat.
Yes.
So it is far more efficient to use natural gas on site just from a greenhouse gas emissions perspective versus plugging in.
Yep.
Now, you can help the electric side by having a heat pump, which creates a COP of somewhere between 1.5 and 3. But if you're talking about getting a power out of your natural gas output, that's something that we need to hear about.
And that's where this is going, because spot on.
I kind of figured.
Nope. Right. Next slide, please. So a little bit about natural gas. All of these charts, is the presentation can be shared with everybody afterwards?
Yeah.
Okay. So there's a lot of numbers and facts and figures, but it talks about some amazing statistics. One that shocked me is for every outage of power, there is 800 electrical outages per year to 1 natural gas. What kicks on to power when your power goes out? The generator powered by gas. The emissions of gas are down 69%, okay, since 1990, okay? They're learning how to burn natural gas and then do it well. And I think in my industry, from a gas burning appliances, 1 kilowatt is equal to 3,400 BTUs, okay? So 1 kilowatt of energy, how electric heaters are rated, is equal to only 3,400 BTUs. So that means that 1 therm, or 100,000 BTUs, a simple 100,000 BTU heater requires 29 kilowatts of energy to match. So it's a 3-to-1 ratio, electricity to gas. I'll hear that again, a 3-to-1 ratio. It is very, very powerful to use natural gas. I go into buildings now when people are saying, give me options. And I say, I can come in with 2 heaters of gas. I need to put in 25 electric heaters. And 25 electric heaters would require 25 circuits and 25 controls and contactors, and the price of this thing just goes astronomical. Natural gas is the best bang for the buck by far. It costs about 1/3 of electricity, and it gives you about triple the energy output than does electricity.
And forget the first cost or the utility. If it's strictly based on greenhouse gas, putting natural gas in infrared heaters or whatever your gas source is will actually produce less greenhouse gas, which, like, people go, that doesn't make any sense. But those are the facts.
And thus trains full of coal. Somewhere, somehow that's getting burnt to create electricity, right? So we got to remember it. I know that there's a place for electricity in cities that are congested or where smog is an issue. But in terms of absolute power creation, I think the best thing they've got going right now is natural gas. Now, I will tell you what's really pretty cool. Pay attention to hydrogen, okay? All right, Boeing is going to fly their first hydrogen-powered airplane in 2027, 2028, strictly by hydrogen. The byproduct of that is water, okay? It's very, very rich. It's very, very volatile. The molecules of hydrogen are 1/100th the size of natural gas. So it's a huge problem from distribution. And I can tell you what's already happening. Toronto, the greater Toronto area, GTA, right, has already provided all of their piping in that area that allows a 20% mix of hydrogen into the natural gas. We in Europe are already being told we have to make heaters that burn 20% hydrogen and 80% natural gas. So they're blending, okay? Now, this is really a big thing. I don't know when the infrastructure will be solely hydrogen. That's going to be years and years away, and it's very difficult to combust. But mixing natural gas with it is kind of the best of both worlds. We can do that now, all right? And we are. The Europeans have a bigger problem. They're trying to get away from natural gas. Why? Because most of it comes from Russia, right? And they're trying to break away from it. They're finding their own wells out there which have different properties. But the supply of natural gas here in North America has us energy independent for the next 80 years. And I feel like right now, gas is such a bad word. We got to remember with our infrared heaters, if we can burn it clean and we can use it effectively, we have a winning situation, a winning combination. And as we start to mix in hydrogen into the combustion process, it's only going to get better. Next slide, please. So what does this mean? In my opinion, energy conservation. It's telling my kids to go down the basement, turn off the lights, okay? It's trying not to use more energy than you need. And this is really what infrared heaters are known for, okay? We have all kinds of studies and facts and figures. They're in the ASHRAE Fundamentals Handbook that basically states a 20 to 30, sometimes 40% fuel savings. The more the air changes, the higher the building, the more we can, with infrared heating systems, impact the overall energy consumption and energy conservation. So we can burn less gas and we can effectively heat a big space. Next slide, please. So this is just a clip, and I don't know what Wisconsin has. Again, I was doing this presentation this weekend, but there are about 50 to 60 utilities that offer a very generous rebate to use infrared heaters. In the state of Michigan, my Michigan dealer draws $1 million of rebates a year. Think about that. He services the eastern half of Michigan. He pulled over $1 million of rebates for putting it infrared. He loves it because he's able to charge more money for his heaters, and he does all the paperwork, but the utilities essentially are providing a healthy $500 to $700 per heater rebate because they want infrared heaters in their energy conservation initiatives. If you look at your utility bill, if it's like most places, there is a recovery fee. It's a small fee that's charged every month. That goes into a pool that they have to spend. Utilities are committed to spending it every year to allow for energy, green energy technology to be put into place. Next slide, please. Okay, so the theory of infrared. If you look on the handouts I gave you, and I sent a lot, but this book right here is really a cool piece. It's our engineered catalog. It's designed for consistent presentations to the engineering community, and it's really PDH. It's the fundamentals for our PDH presentation. So I just grabbed clippets on this slide of it, but we kind of start with chapter 1, which talks about the theory of infrared. Then we talked about the types of infrared. By the time we get to chapter 6, you're either all asleep, I'm tired, or we were learning about efficiencies, right? So hopefully that is where we're at by chapter 6. But let's talk about the theory, which is chapter 1. If you want to follow the book, make some notes. Next slide, please. So the easiest example, and those of you who see my presentation at Detroit, let's just say this is a cooking top right here at your home. All right, you turn on the stove. I burn my hand if I touch the stove. Why? Because of conduction, right? All right, I'm directly touching the matter. If I hold my hand directly above it, okay, how does my hand burn? It takes a little longer. It's because of convection. The hot gas is rolling off of it, right? But what if I hold it off to the side? Okay, I still feel heat. What heat? I'm not in any air path. I'm not touching it, but my hand will burn because I'm holding it off the side because of the radiant output. So the sum of all heat is a combination of conduction, convection, and radiation. Back to my original slide. How efficient are your heaters? We're going to keep coming back to this theme because in a perfect world, an infrared heater would have 0 conduction, 0 convection, and 100% radiant. Right? That would be the perfect radiant heater. It doesn't exist. As a matter of fact, our standards say the most they recognize in the current standards for testing radiant output is 70%. The other 30% is mixed over convection and conduction. All right. So let's remember that. Touching that stove. Hot because I touched it, hot because I kept my hand above it, and hot because I kept it off to the side. And we, as the manufacturer of infrared, want to try and emphasize radiant heat. All right, next slide, please. So when we do that, we put a hot surface up in the ceiling, okay? And the infrared rays travel, just like the sun's rays travel. They come through, they strike the atmosphere, they start turning into visible light, and then they strike the earth or an object. and they turn into effective heat. That's the infrared rays that are emitted from the sun and travel through space. Space is what? Cold. Space is dark. Okay, not until it strikes an object does that change. You should have heard the guy I spent that time a week with on the NASA. He said every hour they circled the Earth, and the expansion and contraction on the shuttle from super cold because you were in the dark to super hot because the sun was seeing the shuttle. And he says that was the hardest part to get used to for the first day or two because you didn't know if the vessel was going to break or not. So it was pretty cool. And the opposite is when we stick a hot air blower heater high up in the ceiling, heat rises. Okay, if the heat never gets down to the floor, we waste a lot of energy to keep it 100 degrees at the ceiling so that we can keep it 70 degrees comfortable down at the floor. Why not try and keep it comfortable at the floor as your first go-to versus the opposite? Next screen, please. This was a study we conducted some years ago. It won Aire Paper of the Year, and it was a 3-year study that talked about infrared against hot air. What was really interesting about it is in the first year we did it, we switched the study every week. 1 week infrared, 1 week hot air, 1 week infrared. We couldn't figure out why the numbers weren't coming out to what we know. With the flywheel effect. When we were switching every week, let's say we switched on a Sunday, Monday or Tuesday, the infrared that was still trapped on the floor was benefiting the unit heaters. By the end of the week, when we went back to switch again, the infrared heaters had to make up for what the hot air heaters couldn't put in the slab. So we realized we had to adjust it. The next year it ran all hot air, the next year it ran all infrared. And then we zeroed it out. We compared for degree days and the temperatures that were recorded. And we documented a 23% fuel savings using infrared. And this was published by Aire as a paper of the year. We were given an award for it. Next.
Did you expect 23? Did you expect more?
It's such a function. I bet you we could have done better if it was a taller, higher ceiling, leaky building. Okay,
Right.
So, but this was maybe it was a small shop with lower ceilings. This would have been in line with what we see.
So theoretically, so that was a 20-foot shop, 20-foot tall.
So it was like a 2,400 square foot, 60 by 40 machine shop.
Okay.
It wasn't huge.
Right.
But with ceilings of 14 foot. I think if this had been an airplane hangar, 6,000 square feet up high, we would have seen notably more. As a matter of fact, when we bought one of our buildings in Detroit, my dad tells a story. He came in, it was a bus terminal for the public transportation in Detroit. So he went, first thing he did is he fixed the broken windows, then he sealed the doors, and then he put in infrared heaters, and all of a sudden our gas bill was 80% less, and they thought we tapped off,
Right.
We were legally bypassing a meter. The inspection. So a little bit of it was infrared, a little bit of it was just, energy conservation, right? Next slide, please. So the other benefits to infrared too is, in addition to reduced energy consumption, low harmful emissions. On the slide earlier, the NOx rates on our heaters, okay, nitrous oxide, one of the harmful emissions that they're really trying to get rid of in this because it does such harm to the ozone layer. But the NOx rates on this, most of the infrared people are working at a less than 100 parts per million. Awfully clean. And our tubular heaters are down in the 40 to 50 parts per million. Certification allows 400 parts per million. So we're doing 1/10 of what we're allowed with the technology we use. Thermal comfort, if you need to heat somebody at a workstation, you don't need to heat the whole room. You need to heat the person at the workstation. If you need to stack a loading dock, or in our case, a golf bay, where it wasn't enough, we can put heaters where we need it. Indoor air quality, flexibility, and air stratification. I am a big fan. Heat still rises, okay? We still give convective heat off of the heat. I'm still a person who likes to move air in the building during the winter. HVLS, high velocity, HV, yes, trying to think here. They go slow. Big fans, they go slow.
High volume, low speed.
Yep.
High volume, low speed, thank you.
But
We're
probably would kill
big
me.
fans of the little air pairs here.
Yeah, thank you. But they help.
Big
Yeah,
fan.
it still helps, mix it up. So,
See what he's in there.
next slide.
Making sure we're sticking with our brands here.
Yeah, sure. So we do 50% industrial applications. We probably do 20% agriculture where they raise chickens and hogs. Okay, that's a big business. Nebraska, Costco decided they got tired of trying to buy chickens from local farmers because they didn't know if it was really organic. They didn't know if they were going to get the supply they needed. So they put a huge operation out in Nebraska that the order for it was 16,000 heaters just to raise those birds that are in the back of the Costco stores. They want you walking back to buy the $5 chicken because on the way out you buy $100 worth of stuff. So that is a big part of our business, livestock. But we do a lot of patios, a lot of military bases, auto dealerships, loading docks, and through COVID, a ton of outdoor patios, right? We are the go-to. If you're not heating a restaurant, you're missing 6 to 8 weeks in the fall and 6 to 8 weeks in the spring that people could be outside having a drink and, participating and bringing in revenue for the restaurant. Next slide. These iPhones are pretty cool. Oh, go back one. You can buy a little device, $60, that actually shows the infrared now. These forward-looking infrared FLIR cameras, you plug it into your iPhone and you can go see. So we like going into places and actually showing people the infrared that's actually absorbed in the material. Okay. One of the big projects I got going right now is down in Mexico. Why do they need Mexico or heat in Mexico if it's not that cold? It's because the steel that they make down there, and they make tons of steel and store tons of steel, it was sweating. Okay, and if the steel sweats, it rusts, and they can't send out rusted steel. So they're heating the steel warehouses just to prevent condensation from forming. They're managing the temperature and the dew point by that. And they're doing it because the steel slabs that would look something like this are absorbing the infrared and thus don't allow condensation to form. Next screen. Okay, types of infrared.
We're just trying to,
Keep everybody.
yeah.
Me too. It's working. Next one, next slide, please. So types of infrared. All right. Normally I show this slide, it's the electromagnetic spectrum. All right, and it's symbolic of all the rays, electric and magnetic, that are emitted. And there's two elements to it. Most of the rays come from the sun, but not all of the rays. Okay, the different rays are emitted, but let's just say that the sun is the primary emitter of this. But there are gamma rays, X-rays, ultraviolet rays, visible light rays, infrared, microwave, and radio waves. And the lines that it moves at are also symbolic of the heat energy that comes with it. The common denominator to this whole chart is temperature. Okay, so you start getting into gamma rays, which are measured, X-rays and ultraviolet rays. But as we get into visible light, you can see it looks like a rainbow. You've got the blue on the right, you got the red on the left. The photographer, William Herschel, I always want to call him Herschel Walker, but I know that's not it. William Herschel was the photographer, the king and queen back in the 1700s, and he was trying to figure out how to get better pictures. And in the process of him working with lenses, he took a prism and he split the light using a piece of glass, like a crystal, and he was able to measure different temperatures. And as he measured the temperature, he recognized that the red was hotter than the blue. But past red was the hottest temperature recorded. And that is because you're in the infrared, range. Infra, silent, red, color. But once you break out the infrared range on the electromagnetic spectrum, you'll see it's quite a large part relative to lighting. All right. But within it, there's visible light, there's short wave, there's medium wave, and there's long wave. And why do I say this from a practical standpoint? Because our heaters are just that. If you want to order a shortwave heater, the only option we have for you is electric. Okay, and I can tell you that many an engineer or a rep has gotten themselves into trouble by trying to get the most amount of kilowatts on the shortest, cheapest heater. And what happens is you put this shortwave infrared heater over somebody on a patio and it's like a floodlight is on them. There's a ton of visible light. There's very effective heat, but there's a ton of visible light. Very often people don't want the visible light. Maybe it makes sense at curbside at a check-in or in a parking garage where the light is helpful. But on restaurant patios, it's not a good fit, even though it provides the most output for the amount of heater you buy. So the next one then we get into is medium wave infrared, okay? In the short wave, we're looking at temperatures around 2200 degrees Fahrenheit. Now in the medium wave, we're operating typically in the 1600 degree Fahrenheit range. So what does that mean? It means that when you walk into a building at night, you can look up and see an orange glow, an orange glow, an orange glow. Very often, the medium wave heaters are ceramic, but there's also lighting and electric heat options that provides an orange glow without the visible light on the floor, okay? And then as we get into the last of the infrared waves, it's the long wave. And who wants to guess what a long wave heater would be?
Tubes.
Tubes, there we go, right? Tubes, because a tube heater that's working properly shouldn't glow. Shouldn't.
So your short and medium wave infrared, I don't think we don't use it very often here, but it's basically a light bulb with a reflector.
The short is electric. And
I know it's electric, I'm
Yes,
just,
but the
okay,
medium is not. The medium is all your patio ceramics. Huge, that's what we've been making since 1955. Okay, and that is the same, and it's a function of temperature, but because you're up in the 1700 degree range.
so that's like a resistive element that you're creating a radiant
Open
effect and
flame.
reflecting.
It's an open flame.
Okay.
But with the tube heater, we're trying to pass a flame down the tube, and the tube temperature, in order for it to be the divide between medium and long wave, there's a temperature limitation of 1350 degrees. And if we stay below 1350, we're considered long wave or low intensity infrared. Just think about the names. We have low intensity infrared, we have high intensity. It's simply a function of temperature. So as we look at this whole entire chart, it's temperature. Okay, as we go down in temperature, so changes the type of infrared that's being put out. Let's go to the next slide. I think we'll start tying this together. So this is a ceramic heater. This is what we've been making since 1955. This is how we got our name Reverberate. We're bouncing energy that's coming off the ceramic with open flames onto a rod. We're bouncing it back to the ceramic emitter. And the temperatures of this heater stay above 1350 degrees, okay? And we limit it to about 1800 degrees. What happens when you get past 1800?
Melt the
Aluminum
box.
starts to melt. Yeah. Right, so it's difficult to manage in terms of, in the design process, but we know, obviously doing it for as many years, how to pull it off. This was all infrared was for the first 40 years. There was no such thing as a tube heater. It was ceramic, okay? And these are still very popular today. But as buildings got tighter, as ceilings got lower, as people wanted to store stuff inside of buildings, these particular heaters, especially in this market, this cold market, became less popular. But if I were to move down to Texas or Alabama or Georgia, go south of the Mason-Dixon line, these types of heaters are all day long to go to because they're very effective. That heater right there, it's about 3 foot by 2 foot and it gives out 100,000 BTU is what you're looking at. A lot of energy for a small heater. Next slide. I'm not going to go through this in great detail, but the BTU range is shared. Controls are optional. Probably what I want to point out is mounting heights, 50 feet all day long. We do it all the time. Airplane hangars. As a matter of fact, I was at a facility in Russia and we were putting heaters. It was 120 foot off the floor. They had a mezzanine level in the middle and we did a second row. Problem with these ceramic heaters, okay? This particular patio and this particular DR series heater, You cannot direct vent the heater. There's no way to get the products of combustion out directly. So you have to introduce ventilation into the building, okay? This is also true for tube heaters. People think you have to vent a tube heater. You don't. You just have to provide 4 CFM per 1,000 BTU. And that is an answer, you know, to a lot of complicated problems. The thermal incident in Montana, had they just not vented the heater, we wouldn't have had a big $2.5–3 million losses we're navigating through right now. I'll share a little bit later on that. They didn't know. A lot of people don't know. A lot of people think that you have to vent. You don't. Okay, and all the codes generally are supportive of that. Next slide. Okay, as we get into a tube heater, there's some definitions I want to point out. The first tube is referred to the combustion chamber. Okay, that is where the flame impinges on the steel. That combustion chamber is usually made of a greater steel material. It's typically aluminized at a minimum, sometimes titanium, and sometimes stainless steel. It's all a function of how much flame we're going to put on that first tube. All right, and then we have radiant emitters, and then the last tube gets a baffle piece put in the inside to slow down the gases. Because the common challenge that we have, and I'll come back to this, is that that first tube is hotter than the last. And people think the heater isn't working properly, that it should be perfectly even. It's not. But we, when we design them, are trying to figure out how to manage that. The other thing is the length of the heater is often a function of how much energy we're putting down it. If I have 50,000 BTUs, I may only be able to go out to 4 pipes. If I have 200,000 BTUs, I can go out to 9 pipes. Okay, so it's a function of how much energy in, so that when we get to the end, we're in the target window that we need to be. Next slide. Quickly, because this comes up in the market a lot, there are different ways to move the flame down a tube, right? The most popular and most economical way is we put a fan in that black box, the burner box, and it just pushes air down the tube that moves the flame. Next slide. Okay, the next slide shows an exhaustor motor at the end, okay? The exhaustor motor simply pulls it through the system. Now, our friends out of North Carolina, gas-fired products, they love to sell that this is a better way to move air, okay? But they can't explain why. The infrared output's relatively the same on either heater. The advantage to putting a pump at the end is that you can often put vent lengths double what you could otherwise. Because at this point, you have velocity. You're moving. So if I need to vent 40 feet away from where the heater is, putting that type of system in makes sense. What is also unique about this picture? What configuration is that heater in? A U shape. That means that that hot tube where the flame is impinging is directly opposite the cold tube where the baffle is. Right? If you're heating for comfort, you're trying to heat picnic areas or golf driving ranges or outdoor patios, go to a U-tube, because the U-tube will keep you out of trouble and it's going to be the most comfortable for people. Next slide. And then I don't know how much you see engineered vacuum systems, but this is where we tie up to 6 burners into a vacuum pump. Typically Amazon, FedEx, large military projects, okay? This is a complicated system that has rules and design, and we help at the factory. But the engineered vacuum system is an answer if you want to minimize vent penetrations in a building. Also, if you don't, if you have large, if you have rules that in large spaces, you just don't want any of the vent penetrations coming out, perhaps the front of the building. You pull up to a curbside building and you don't want to see all the pipes coming out. Vacuum systems allow you to do it. And the last thing that I lost my train of thought, you can change up elevations on these systems. So like FedEx uses these and they're able to dip the systems below their conveyor belts. So you can go up, you can go down. And because of the engineered attributes of this, you can do a lot more. It just costs a lot more. Next slide.
You can also avoid the whole limit the number of vents by putting some makeup air in the building.
By putting
Exhausts and
yes,
makeup air.
sure you can. Yep. Anyways, the chart pretty self-explanatory, different features. We make all kinds of tube heaters. You know, we have a good, better, best approach. And I shared already the temperature and the venting rules. Not too much that's new there. Next slide. Okay, we're already talked about that. Next slide. The next slide. Okay, design principles. All right, this is chapter 3 in your handbook. You want to go to this. I'm going to touch on the first page of it. Yes. Okay, next slide, please. What do we do when we need to design with infrared? We need to conduct a building survey, right? And that is our values of the roof, insulation, floor, is it insulated, the whole use of the building. And I chuckle all the time because people spend so much time on what are the doors insulated, what is the R value of the roof, is it a 28 or a 30, what are the walls? But nobody ever knows how many air changes are a building. Okay, an air change is generally speaking 50 to 70% of your heat demand in a building. And really, there's no real way to know what the air changes are. Now, maybe you can get an engineered system to make other stuff you do or know. But as a whole, when somebody calls and says, I've got a building that's 60 by 40, I've got a building that's, 60 by 200. How much heat do I need to put into it? The primary driver is how many air changes are in the space. And I can tell you when we do a survey, if I'm on the phone, I use a rule of 50. If the building's insulated, for me to get talking points, I multiply their square footage times 50. And if I do that, it gives me an idea of how many BTUs need to go in that space. If I've got a 1 gallon bucket in front of me, I need to pour 1 gallon of water in it to fill it, right? Anything short, it's not full. Anything more, it's too much. All right, so we look at what the supply is, and I can tell you for the sake of qualifying a customer, 50 BTUs per square foot is good. But when we're doing a survey for infrared, I want you to look at, are there cranes in the building that might park right below a heater? Are they gonna put racking up or down? The racking is gonna have stuff stored too close to the heater. Are there sprinkler systems in the space that we need to work around? There's a lot of things that with infrared, because of how it works, we have to consider in this first phase. All right, next slide. All right, this one is where I've found through the years I've gotten better and better at. True story, we sold patio heaters to a restaurant owner in Minneapolis. They put them out there, they thought they were great, January hit, and they couldn't put their restaurant patrons outside, but it was heated. I said, are you kidding me? It's 0 degrees and the wind's blowing. You expect the heaters to work? Yes, they did. How did we get there? And it comes down time and time again to expectations. All right. I will tell people now when I'm driving, you saw this with the golf range. If your expectation is to give you a 15-degree temperature rise under a 5-mile-an-hour wind, I can do it. But if your expectation is to put golfers on that golf range when it's 20 degrees and the wind's blowing, super hard, I can't do it. Your expectation on the tube heaters, if you put in one heater, you're going to have a hot end of your building and you're going to have a cold end. You tell people on the front end what to expect, and they're often very happy with what they get. It's when they buy a heater off the internet and they don't have their hand held by professionals like are in this room, why we get in trouble, okay? I have a policy, if somebody orders an 80-foot long, 200,000 BTU heater, so that's our longest and our highest BTU. If it's just one heater, I make the customer get called. Not the rep, not the distributor, but the customer. Well, why are you buying one 80-foot heater? Well, my building's 100-foot long and I don't want to buy 2 heaters. Okay, let's stop. Instead of buying one 80-foot 200, how about we buy 2 40-foot 100s and balance the heat? And you're still buying the same amount of pipe. This is going to allow you to have a balanced building. And if they say, yes, thank you for telling me, and often they do, we go forward. But if they say no, never do they call back because they were told of the potential of what they were doing as being wrong. Expectations matter. Next slide, please. The other and last thing that we'll focus on, we have recommended mounting heights. Okay, the bigger the BTU of the heater, the higher the heater goes. And that's published in our manuals. It's published with some charts inside of here. I encourage you to pay attention to that, because if you follow our recommended heights, very often you don't hear back from a customer who's not happy. It's when they put too little heat up too high or too much heat down too low, we have a problem. And as a rule of thumb, if the heater is 12 foot off the floor, that's going to give you a spread of 24 feet left and right. Okay, double. If we're 20 foot off the floor, we're 40 foot left and right. Our competition likes to poke holes at us, and I've seen it happen a number of times, to the point some of my dealers have asked me to stop publishing this. And they try and say, oh, Detroit radiant heater can't go at 16 feet because their manual says 18 feet. Well, that's recommended, okay? And we do that based upon experiences. But if you have an application like a car wash that you want to put in a ton of heat down at 12 foot because it's a wind tunnel, that's fine. Nothing's stopping you from doing it. It's just a matter of coming back to what expectations are and a good customer experience. Next slide, please. High intensity heaters have a very intense heat zone, but they're not that great. Next slide. This would be a bad design where they're placing two high BTU heaters in the center of the building, where if we spread it out to smaller heaters around the perimeter, we're going to have more coverage. Okay, next slide. And the way we do that, and this is in the book and this is in the manual, we have dimensions A, B, and C. And if you look at A is the height we recommend, B is the distance between the heaters, and C is the distance between the rows of the heaters, okay? When you come to Detroit, and those of you who have, you know that we spend 4 hours just on designing with these charts all alone, how to do this. I don't have the time today to do it, but I want you to know there are charts that can help you apply infrared properly. Next slide, please.
And the basics behind this, as I'm looking at it, would be match where the load is, not where the people are.
So the primary thing with infrared that we try and push is perimeter mounts. Okay, and then I think you also have to be mindful of where the people are, because we're allowed to zone heat with infrared. So yes and no. If it's total building heat, go perimeter first, center second.
Got it.
But if it's spot heating for
We
comfort,
have a roof load, so
right? Yep.
yeah, that's where the people are too, underneath the roof.
Next slide. Okay, we talked about this. I think this is really important. I want this really, kind of stuck in your head, hot end and cold end. You get that call 2 or 3 times a week from a customer about why it's hot and cold end. All right. For us to vent a heater, the standards require us to be less than 480 degrees. Okay, so everything on the end of the heater is based upon our certification, which is a minimum of 232 degrees and a maximum of 480. What is 232 Fahrenheit? The boiling point of water. And when you drop below 232, condensation starts to form. That's why the standard says for a dry heating system, you have to stay above 282. That's why a lot of your unit heaters, Modine and Resner and us, operate in the 80% thermal efficiency range, because if they push it too much more, they start to get condensate, and they're not equipped for the condensate. The hard part with infrared heaters is, as we get further down, I am getting better efficiency values, but I'm getting very poor radiant heat. A tube temperature at the end that's only 100 degrees or 200 degrees is not emitting any radiant heat. Our body temperatures are 100 degrees. Remember, radiant heat is a function of temperature to the 4th power. So you want hot. So sometimes we compete with how the heaters are certified with this end number that we must chase versus the reality of a good radiant heater. See how this goes. I'll see if how we do it on time here. All right, next slide, please. So some good design practices are here. All right, this application up there really happened. The heaters were actually designed by the engineer to have the burners down on that corner. But when the contractor got to the job site, where did he find the gas lines? On the other side. So he put the burners down where the gas is, which is very common in our industry, go where the gas is closest. And then he turns on the heaters, and where all the load was down by the overhead doors had no heat. So how did we fix it? Instead of ripping out the system, we simply broke the system in the middle, added burners on the corner. We didn't add any more pipe. We didn't add any more BTUs. We just balanced the load, okay? Balancing the load is key. The other thing that we see a lot of in firehouses, ambulance space, trucks for garbage, these city buses, is people like to run the heater directly across the base. And that's a hazard because often those trucks are quite tall. And also it doesn't allow the infrared heat to get down to the floor. So you want to stay out of trouble, put it between the base and run it parallel to the base. Okay? These concepts are what our design book touches on, as well as the videos. Each one of the chapters of that design book is on YouTube. So you could go to YouTube and watch any one of these videos on design. It's a 4-minute clip. So you can watch our whole book in about half an hour. There's 7 chapters reading. It's worth doing so. Next slide, please. Same thing, like the DR chart, there is application guidelines that gets into the A, B, and C, mounting height, rows, and distance between heaters. We can come back to that. Again, we have a whole booklet specific to design. We don't have time to cover it today, but know that charts exist. Next chart, please, slide. All right, safety. Next slide. All right, that's where I was in Montana. It was a wood where they make lumber, okay? Acres and acres and acres of cut down trees, and they had a fire, all right? And you can see the roof all discolored from the fire that happened. And this was ironically with a unit heater that we just sold about a month ago and had been in service for 3 days. So how's a brand new unit heater in service for 3 days take the whole mill out? Sad part about it was the 3rd fire they had in 10 months, and it put them out of business. So 85 people lost their job. Okay, so there's all kinds of attorneys swarming on this one. Loss of business, all the lumber they want. You know, it's not the damage of that ratty old building. They want the whole operation as part of the loss. So it got my attention, and that's where I went out there. I want 4 takeaways on safety, okay? And I want to scare people with infrared. I don't want to scare people with heating, with gas, but you got to think. And the ones that typically I end up going to fire losses, and I do that about once a year. It's usually somebody trying to do something on the cheap. They don't want to buy the right vent kits. They want to buy more heat than they need. They don't get asked the right questions, and they do really shoddy work. Almost every time the problem comes down to find a cheap contractor that nobody else is willing to work with, and bad work gets done. So I'll show you the slides that I want the takeaways from. Next slide. First, there's a book that we, as an infrared industry, can I hold that real quick? Sure. We put this out, we print this in accordance with AHRI. I am chairman of this committee, the Infrared Heater Safety Council. It's the industry trying to come together for safe practices of heaters, right? So that's our go-to. We send those to fire marshals, insurance agencies, and to plant managers, but that mainly goes out about once every year and a half, once every 2 years. But it goes out to about 30,000 people trying to promote the safe use of infrared. It's very effective too in the courtroom, part of our defense strategy. Next slide. You need to understand clearance to combustibles. Now, unlike our minimum mounting height, clearance to combustibles is the distance that we must keep away a combustible item from the heater. That's mandatory. If we keep that distance, we won't have problems. So every heater has a top clearance, a side clearance, and a bottom clearance, okay? And what we're paying attention to is canvas awnings. We're looking at cranes. We're looking at racking. You know, in that lumber yard, are they storing lumber too high to a heater? Okay, there's a lot of things that go into that. But the clearances are mandatory. How we get the clearances on the next slide, please, is we hang a heater inside of an apparatus that's all painted black. Those of you who have been to our lab have seen it. And it has thermocouples embedded throughout. And we run the heater for 2 hours. And when we hit the saturation point, it doesn't get any hotter. We measure the distance at which point we got a 90-degree temperature rise. 90 degrees. So if the lab is 70 degrees, we stop recording when the thermocouples read 160. And then 90 degrees is what the standard calls for. So when people say, hey, what's the temperature of the heater going to be at 18 inches off to the side, 13 foot, I have no clue. Okay, we sometimes can run a test, but as to how the standard works, it's a 90 degree temperature rise. That'll give you a clue. Probably one of the biggest problems we have with sprinklers is on patios that are sprinklered. Okay, because the trip point on a lot of sprinkler heads starts at 160. So if you have a 60 degree night, putting a heater plus 90, you're pushing up to the limits of when it is. So you can get different color sprinkler heads. And very often on the sprinkler heads for patios, I recommend the red one, which is 230 degrees. It keeps people out of trouble. Next slide. The requirements now for installing an infrared tube heater are that we, the manufacturer, must provide a flex hose, and the contractor must install it in a C configuration, just like that. There's no getting around it. I can't tell you how many times I see that not done right. Still, that's it. Why isn't the C configuration? Somebody want to guess? Expansion. Okay. Expansion and contraction. Each cycle of an infrared heater on or off is 2 to 6 inches of movement. Okay. That configuration allows for the movement. We had a problem in Minnesota. The codes were improperly written. A lot of the contractors thought they needed to run copper directly to the heater. Expansion and contraction work hard. It's like taking a coat hanger and bending it 15 times. What happens? It breaks. Okay. Propane is under high pressure. Very often in the building, 2 pounds of pressure, and it quickly dumps and it creates an explosive environment. We've had, unfortunately, some explosions, and thus the industry stepped in, and this gas connection still remains key to much. Next slide. Okay, venting the heaters. This is where people don't understand what they need to do. And if you look closely at that picture on the right, that's what I went there in Montana for this week. What they did, instead of venting with the thimble and the double wall vent pipe and the whole thing that we have depicted with the proper pieces, is they bought a plumbing apparatus that sealed it. And guess what the plumbing through the wall shield was? It was rubber. You can see the rubber right here around it. Rubber up against 400 degree vent pipe resulted in that happening. So this is the third time I've been to an incident due to improper venting. If you're going through a combustible wall, if you're by a 2x4, if you're going through insulation that could potentially, harness the heat energy, you've got to make sure you create spacers. Even if a company comes in and they have the heaters hung in their attic and then they come and they have it blown in afterwards, someone's got to go around the vent and create the air gap around it so that the heat doesn't trap it. Especially with that, that they shred paper with water and they spray that stuff in. I don't know the name of it. That stuff is bad around vent pipes. And I'm not talking just our stuff. I'm talking heating as a whole. Everybody has this challenge. And this is an ongoing challenge for us as an industry. Next slide. Regular maintenance. The heaters can't do, what they're supposed to do and the way they're supposed to do unless they're kept clean. And I can tell you that infrared heaters are pretty doggone forgiving. We put these in some of the harshest of environments. Car washes are really tough. Agricultural swine barns are really hard. Swimming pool environments. And the nice thing with any of the heaters that we make on the tube or the unit heaters is we can bring fresh air from the outside in. So having the ability to duct in fresh air will dramatically reduce the maintenance that's needed. But if the heat exchanger gets all full of crud, it starts harnessing the energy and eventually the heat exchanger can fail. So once a year, we try and put a lot of tools out there, videos on YouTube, all of our manuals, troubleshooting guides. We're really good about answering the phone. We encourage people to, once a year, go look at the heater, typically in the startup season, and make sure that the basics are there. Does the fan have a ton of crud, accumulated on? Is there a bird's nest in the vent pipe? Is there, a lot of dust or sawdust that accumulated in the operation or oil over the course of their summer season that just is gonna start, burning as they turn on the heater. So look at that. All right, next slide. There questions about safety? Again, I've had some people say you scare people. I don't want to scare, but I want the idea that hook up the gas properly, vent it properly, do a little bit of maintenance and maintain clearance to combustibles. Those are the 4 takeaways. You do that. I don't care if it's infrared or hot air, whatever heating, you're not going to have problems. All right. Just make sure your contractors too, hold them to task. Why aren't you getting a vent kit? Well, how are you going to do this? Ask questions. Okay, because you have an obligation to some degree to help the system work better. Engineers and contractors, I'll say this to the engineers who are listening. The National Fuel Gas Code requires that signs now be posted around infrared heaters if they're stacking stuff in the room. How many people know that? All right, so if you're writing a specification, you should have that in there. Contractors shall supply signs notifying of the risk of stacking materials too high in the space. All right, and that's fine, the signs work. Out in Montreal, we have to put laser beams that if something crosses the laser beam eye, it shuts the heater off. I mean, they're pretty strict about it in other places. Signs work, okay? Next slide, please. Okay. This talks a little bit about the construction of a heater. When we take a pipe, all right, let's say this is the pipe right here. The first thing I'm looking at, what is this pipe made out of? Is it made out of stainless steel? Is it made out of aluminized? Is it made out of titanium? Okay, because each material has its own ability to conduct energy. Stainless steel is very poor at emitting heat. Okay, if you're actually doing something with stainless steel, I often encourage you to increase your heat load by 15% because stainless steel harnesses that energy. All right. The next thing that matters with the pipe that we use is the cost. If I did all titanium, we wouldn't be able to sell a heater because it wouldn't be affordable. We have to balance cost. So how does the material conduct energy? How much does it cost? How good is it protection against rust? The economy heaters out there today are all out of hot rolled steel tubes, but hot rolled steel will show rust in just a matter of a couple months. The go-to for the heating industry is aluminized steel, where they take regular steel and they put some aluminum in the baking process, like making, cupcakes. You mix the batter. When they mix the batter, they put some aluminized material in it, and that prevents it from rusting. Okay. The problem with aluminized, what color is it? What color is aluminum? Silver. Okay, silver is not a good energy emitter. Remember, so we have to address that. And finally, the emissivity, okay, and that is a word, is energy in, energy out. That space shuttle re-entering the atmosphere. The energy is coming into the space shuttle. It knows it's coming in. It's saturated in probably 2 minutes as it goes through the atmosphere. What it wants to do, and the reason it painted it black, is it wants to release the energy. So while black absorbs the energy, it also releases energy the quickest. So those 4 things are what matters when we talk about a heat exchanger. Next slide, please. Next thing we look at is how thick is it, all right? You're gonna see in the industry, some people use 20 gauge, some people use Schedule 40, they're spec lockers. I would tell you that the bulk of the industry is on 16 gauge steel. That's about the thickness of a nickel, okay? That's a good balance between a good quality pipe that's gonna last and price. Next slide. We look at this chart, I could spend a whole 2 hours, really bore you, about the different properties of all these different materials. But just know our economy heaters are working with hot rolled steel. And as you get up into our premium stainless steel heaters, you're paying double the price, but you're getting a far greater tube, all right? These heaters ship, they're a lot of weight. So we're looking at, what do people want? If you're in a car wash, you probably want stainless steel. What is, when we talk about stainless steel, you ever teach the group about the difference between 300 and 400?
No.
Okay, it's a big deal. All right, 400 will rust. It's a cheap garbage stainless steel. All right, and a lot of the industry likes to put 400 because they can claim stainless steel. It's still magnetic.
That's what the kitchen guys do.
Yep. That's what they do. But when you're putting heat and you're putting corrosion in an environment, really, the right thing to do is to be in 300 grade.
And for all you guys out in TV land, this section of the infrared catalog that you can watch online or look at it in the book is really fascinating because you go, if I'm an engineer and I go, well, it's a tube heater, it's got a burner, I know how many BTUs I'm putting in the burner, and it's this long. And if that's your level of understanding of infrared, you're gonna get products that are definitely gonna be less expensive. Maybe you make your budget, but your owner's not gonna be thrilled with you if all the heat's coming out of the first tube. And it's just one of those things where just glancing at it and saying it's all the same is really a shame because there's a huge difference in just the quality of the tube, but most importantly, it's the quality of the output that the owner receives.
I agree, and I think particularly when people pay double the heater price for stainless, when their stainless steel heater is rusting in 3 months, I've seen people really upset.
Yeah.
And so make sure if you're quoting a stainless steel heater, and they're very popular, people are building car washes like they're going out of style of late. Big New York money's coming in for that, it's a whole nother conversation. But the idea of quoting R300 against a 400 grade is something that you want to point out to the contractor, okay? Next slide.
Well, it's that, and it's just seeing people use spiral.
You know, yeah, there's one competitor who makes spiral pipe radiant, yeah.
Yeah. They wouldn't tell you that it's inferior, they'd say it works great.
Emissivity, okay, energy in, energy out. The opposite of emissivity is reflectivity, okay? So we want to have a tube that's highly emissive. We want to have a reflector that's highly reflective, okay? So this demonstrates the concept of emissivity. It's a measure of the ability. You can mathematically score emissivity on a scale of 0 to 100. And that's within some of the fundamentals books. Next chart. That's the chart, okay? So perfect emissivity would be a score of 1. And perfect reflectivity would be the opposite. The emissivity is 0. Next slide. Swedge tubes. I think I told you we made a little sign, but the seatbelt scenario, okay, buckle up. We put our tubes together, okay, and that is really a quality feature. The contractors like it because they can put 2 to 3 tubes together on the ground and raise it. If you don't swedge the tubes, then your clamp is acting as the emitter. And on every start and stop cycle, when the heater turns on and turns off, moisture forms, okay, because it has to get above and below the boiling point. And if you have a gap where the clamp is, that's where moisture is going to form. You're going to see early corrosion and failure. Sell our swedge tubes. We put a lot of work into having to do that. Make sure people understand why. Next slide. Polished material versus mill finish. We actually get, has anybody heard of Scana? So Manitowoc, is that, there's a mill, right?
Manitowoc?
Yeah.
Yeah.
Right, I got it right?
You were in the ballpark.
Yeah. So,
Gotta watch Wayne's World again.
but anyways, we get our mill, we get our aluminum from Wisconsin, right? And we buy direct from a mill, and they're one of the few mills that makes highly polished material. Okay, and if you go to the AbsolutAire fundamentals book, highly polished aluminum is going to reflect anywhere from 60 to 90%, whereas mill grade aluminum, which is readily available, is going to reflect only 35 to 60%. The conversation about reflectivity is something that we want to have because a highly polished piece of aluminum is going to show more shine and more reflectivity than something that absorbs the energy. Next slide. There's a lot of discussion in our industry about reflector geometry. Okay, that top big depiction right there is our typical design reflector. The white gaps on that tube are our reverberate concept. We try to bounce some of the energy off the reflector and back into the tube. And by doing that, we raise the tube temperature by about 40 degrees. So from roughly 1,000 degrees up to 1,040. But if you take 40 to the 4th power, you get a much more effective radiant heat output than you would if you had a cooler tube. We have also made a new heater. I don't know if you've been able to see our video, but our REV series where the reflector geometry is set in the field based upon what people want. And we can give you single pass or dual pass. We can send all the rays down on the first try, or we can bounce them back in the tube depending on what the consumer wants. Next slide. Last thing too, two-stage, we patented two-stage, we created it in 1992. It's like the go-to in terms of what infrared heaters are expected of now. But this chart right there shows degree days in all of these different cities. All right, Minneapolis, only 10.2% of the time do you need full heat load. Okay, so you design the building for a worst case scenario. What you end up having is only that needed 10% of the heating season. So I liken this to driving your car in the city versus driving your car on the expressway. When do you get better gas mileage? On the expressway, why? It's the same car, same driver, same engine.
Steady state operation.
That's right. You don't start and stop. Now you think about a radiant heater. It takes about 5 to 7 minutes before the tube comes up to temperature. And that's wasted energy. You're not emitting any radiant heat, but you're burning gas. The minute the gas valve turns on, you're burning gas. Okay, so the idea with two-stage is to stop the cycles. So if we reduce the cycles, and typically with our two-stage, it's 35% reduction. It ends up meaning less energy is wasted in the heating up and cooling down process of cycles. Make sense? All right, next slide. Okay, so we're in the home stretch. All right, efficiencies. Remember I said that question, how efficient are your heaters? And I still struggle with that. And typically when I go into an engineering firm, because I know they want me to leave so they can go back to doing what they're doing, they're being polite. Not all, but when it's 15-minute drive-bys, I answer the question by what efficiency are you referring to? Combustion efficiency, thermal efficiency, radiant efficiency, or pattern efficiency? They're puzzled because very often nobody's explained there's 4 different types of efficiencies that we look at. And then also there's just an operational efficiency. Are we saving the consumer money and providing a comfortable space because our heating system works the way that it does? So we know operational, we already covered it. We're saving 20 to 30% using infrared. But if we dissect the heater, let's look at the different efficiencies. Next slide, please.
Hey, Joe, is there any chance we can wrap up in like 5?
5 minutes, yep. Okay, next slide. Combustion efficiency. How well do we burn the gas relative to the oxygen supply, right? And that's a chart right there that the combustion engineers could understand, the gas engineers. It's called stoichiometric combustion, perfect combustion. Okay, the exact amount of air molecules are there for the gas that's being supplied. And what we want to keep in mind is that while perfect combustion is good in theory, the minute you get a little bit of debris on the fan or you get a bird's nest in the system, you run off that cliff and you start creating very poor combustion, which is bad. So this chart would be what my combustion engineers look at closely. Next slide. The takeaway on this is a burner with a Venturi design because of the way a Venturi works. If you understand Bernoulli's principle, he's the guy kind of attributed with making lift for airplanes and how planes fly. But it basically gets into, as the pressure decreases, the volume of the flow increases. And so why people do Venturis is because as the gas and air are being constricted, they have to accelerate. It creates better mixing. Okay, so the combustion efficiency, you'll notice better burners have a Venturi. Cheap burners are just going to have a simple car, right? Next slide. Okay, thermal efficiency is how we certify to. It's a measurement of all energy, right? Conduction, convection, radiation, radiant. So we're measuring all 3, all right? And what comes in and what goes out. And where does the other stuff go? Typically out the flue, out the stack. So next slide. You already seen this. Next slide. This is the go-to for certification. We measure the combustion of the burner. We chart it based upon the CO2 and the gases coming off the heater. And then we measure it against the stack temperature. Okay. So if I take a 20-foot, 100,000 BTU heater, 2 pipes, 100,000 BTUs, my stack temperature is very hot. Okay, I'm pushing up the limits. And you can see, even if the combustion is the same, where it crosses here means that the heater is less thermal efficient. Okay, so we look at the thermal efficiencies. Unfortunately, this is the only way our heaters are certified right now by the standard. They require us to be 70% thermal efficient. Most unit heaters are 82% thermal efficient, but they're only measuring these two CO2 against stack temps. Next slide.
There you go.
I beat this kind of death, but on that 20-foot, 100,000, you're right at the minimums for certification allowance, but look at the heat pattern. If you're working over a restaurant patio, a 20-foot heater may be better, even though the efficiency numbers aren't good. The heat pattern is much better, okay? Versus a very high efficient heater. All we did here to get the efficiency up was that pipe. Didn't change anything, we just had it. Next slide. Radiant efficiency, no. This formula used to throw me for a loop. I still have to reference it, but radiant efficiency. Total radiant output is equal to A, the area. How big is the pipe? Okay. E, the emissive value. What color is the pipe? The Stefan-Boltzmann constant, which is a math thing to make it work, temperature to the fourth power. So how much pipe? What color is the pipe? How hot is the pipe? Really that simple. But you can put it to a mathematical formula by doing this right here. And we do. Next slide. This is the math demonstrating how we do the mathematical formula. But in reality, the next slide will show our rig. Okay, this little device right here sits on a whole rig, and it moves back and forth, and it's measuring how much radiant output is coming off the pipe and recording it, and it's giving us a visual depiction of any one of our heaters. This is what the infrared industry is going toward. They're infrared factors. Has anybody seen the infrared factor specs yet? So we score SEER numbers for air conditioners, right? It's a marketing number, right? It's all it is. It's a marketing number to compare one's air conditioner against
It's a level
another.
playing field.
Yeah, level the playing. So our infrared factors right now have a score of 7 to 15, but a 7 means 35 to 40% radiant efficient, and 8 means 40 to 45. It's just this chart that has a number. And the reason our industry doesn't want to publish a 40% efficient number is because it sounds terrible. Okay, I can go get a 90% boiler, 98%, and I'm going to buy a 40% radiant tube heater. Okay, it's because that efficiency question is so hard to answer with our radiant pipe. But we have a rig, we measure it, we can get you numbers on our heaters. The industry is moving towards this. It's called the ASHRAE standard 1330. Next slide, please. Lastly, so we can wrap this up, is how well do we lay out the infrared heaters? Okay, we balance. Look at the lighting in this room. There's 4 tube heaters right up here. All right, why didn't you just stick one down the middle and make it brighter? Because it would be very bright in this area, right?
Very tempting.
Yeah. But you have 4 rows, and we, just like a lighting pattern, try and find how to balance the load. Last video. Okay. So when we look at efficiencies, we look at combustion efficiency, thermal efficiency, radiant efficiency, and pattern efficiency. The combination of all 4 makes useful heat, right? And done right, when you pick the right models, you're getting the customer the best value proposition that's available. And I'm going to ask the last slide, I think. Yeah. So we don't have time, but the REV series, it's up for Product of the Year award. It already won the aluminum extrusion Product of the Year. Plant engineering, I hope to win this contest. It's a big breakthrough in infrared. It really does some neat things. The features of the REV heater are all listed on the left. It's a spec locker. I would ask, please watch the video. Okay, we have a features link. It's a 2-minute video. Okay, and then meet the team. The engineers behind this heater has a neat little video as to why we did what we did. But the industry is taking note of this. It's a premium product, okay? And there are benefits to it, but I would tell you the biggest benefit, the radiant output on an equal for equal basis, a 40-foot heater of regular, a 40-foot heater of the REV, we're scoring about 15 to 20% more radiant output. That's it.
How about a nice hand for Joe? We're running a little bit behind. We're going to start our next session, which is going to be with Airius and David at 10:05. So you guys have 6.5 minutes for your break. Hustle back. You guys in TV land. Do, and we'll see you in a few.
Sorry.
Ready to roll. Great. Hey, folks. We've got David Johnson here from Airius. So I don't know. Once upon a time, Airius was like basically the only sort of compact Destratification, did you guys win some awards based on that from?
Yeah, actually several of them over the years, several different awards that came out for innovative design and
Sure.
that type of thing that we came out with. A lot of our clients haven't realized that we've been around for about, doing that particular product for 20 years. Company's been around actually about 50 years, started as a plastic molding injection company. We made all kinds of different things like amplifier cases, stereo speaker cases, things like that back in the day. That was when we started out doing destratification fans. The plastic molding injection was about 95% of what we did. The fans were about 5%, 10% kind of thing. And now it's a switch. We do very little plastic molding injection at all. And it's almost entirely the fans now. That's kind of gone by the wayside, and which is great. And that's kind of what brought me into this market.
Let me just add
Yeah.
real quick. So very rarely, we usually find all the products and then we introduce them to our customers. This is a product that other people said, you should go rep this because it's really interesting. So I don't remember which particular engineer called me up and said, this is the greatest thing ever. They got great videos and that. And so we sort of pursued it backwards from the way that we usually do. And we've put a lot of these in. It's been a great product for us. And so we just want to give a little bit of education of more on the why instead of the what.
Exactly.
All right, sounds good.
Exactly. So yeah, I'll jump in there. My name is David Johnson. I'm the regional sales manager for Airius fans for Wisconsin and Michigan and also the Southeast US. So have quite a varied territory, which is actually really good because I deal with a lot of different environments throughout the country. So originally started out as in college to be a history teacher. Didn't go that way. I was raised in the HVAC field. My dad was an HVAC contractor. Later headed up the HVAC for the school district in Colorado where I grew up. So it was in my background, never intended to get into the field, but fell into it as a residential estimator for HVAC and also light commercial. And then ended up at Airius because after about 18 years of doing that, I looked at what they had, just stumbled across it one day and said, hey, this is a great product that they were doing. And literally the company was 6 blocks away from where I worked. And I said, I need to go talk to these guys. And they were looking for a territory rep. So I went and talked to them. The rest was history. It kind of led me to that 5 years ago. So came in to do that. And it was a product that was out there that wasn't really being addressed in HVAC. If you have any kind of a background in that, in HVAC, seems like they talk about, putting in more returns, variable speed motors, window treatments, things like that, insulation, but they never really kind of address it very well. And when I saw this product, I was like, wow, I didn't even know this existed. When I was in HVAC, I hadn't heard of it. And so jumping over to it, it was a great segue, leaving that particular segment of the HVAC field going over into this was the perfect way to go. So we're going to talk a little bit today about the product that's not so sales geared in my presentation that I do. It's more informative. So I hope you get a lot out of what we'll be talking about today. Okay, next slide. So what we've got here is, we're going to go over the fans a little bit. We're going to talk about thermal stratification, what it is, thermal destratification, how we deal with what stratification is, understanding the technology, what makes this particular fan help with these situations. We'll talk a little bit about HVLS fans versus Airius destratification. It's something whenever we do trade shows like the AHR trade show, we always get these questions. Why should we use your fans over HVLS, or can they be used symbiotically? Well, which is a great question. And then opportunities to look for. If you're walking into a situation, it's like, hey, our Airius destratification fans are going to work really good on this project or in this building or where I'm at here. We'll talk about the product overview. Don't know if we'll necessarily have time for questions and answers, but you can definitely email me if you have questions afterwards, and I'll be happy to shoot back information on that if there are any questions. So thermal stratification, basically it's a natural process, it's physics. layering a temperature from floor to ceilings. So it's hot air rises, cool air falls. That's all it is. It's funny, when I'll talk to clients at trade shows, I'll ask them, hey, do you know what stratification is? Or they'll ask me, what is that? That's all it is. Okay, so recognizing the problem, basically, when you walk into a location, it's like, okay, is it going to work in this space where I'm at? So things to look for: large temper differentials between the ceiling and floor, location and climate, high base spaces, high HVAC supply and return locations, the short circuiting that you might run into, minimal air movement, huge. I remember when I first got into HVAC, they said the most important thing to learn in HVAC was airflow. The second thing was airflow. So it's just air circulation. It was just huge in that. So poor thermostat locations, hot and cold spots, difficulties in reaching set point temperatures, floor condensation, heating and cooling system types that are out there, large amounts of air infiltration. We're going to kind of deep dive a little bit more into those as we go. So here we got our friend George Costanza. He's walking around saying, look, 35% of your energy bill is being wasted within a space of a building on average. It's like throwing money down the toilet. It's absolutely true. There's so much energy that's being wasted in buildings out there right now because things are not being done properly or they're not being addressed. And one of the big major things that we get hit up a lot is overdriving existing HVAC systems. If you've got all that hot air in the ceiling and it's not being utilized correctly, you don't have even temperatures within the thermal envelope or within the space, what happens? The thermostats start getting cranked up. You start overtaxing the HVAC systems that are going on there. And where you run into a lot of complaints with that, or where I do, is you'll hear from schools, organizations that are on a budget. They don't want to have a contractor come to them and say, hey, I know just a few years ago you bought this rooftop unit, but we're going to have to replace it because it's shot. And it's like, wait a minute, I thought I was supposed to get 15 years out of this. Nope, sorry, you didn't. It's time to replace that because it's been overtaxed and overused incorrectly. We want to address how we can help with that situation coming up there. And, and again, doing that, it's going to cost them more money if they have to keep replacing equipment prematurely. Occupant discomfort is another one that's there. You get a lot of complaints in certain applications, certain projects that are going on out there where you've got different workers, different clients will come to us and say, hey, our people are not comfortable here, especially in climates like what we have here, in Wisconsin or in Michigan that I deal with, or even in Colorado where I'm from. Colorado's not that much different than your guys' weather here. Very similar with that. Even down south, where you run into, the hot weather down there. We'll be talking about the differences between climates like up here and climates like in Florida, which is another state that I deal with, and how destratification affects that area as well, because you're going to kind of be surprised by that. Next. So thermal destratification. Destratification comes in installed at the ceiling height, sending air down to the floor in a slow moving column, equalizing the temperature from floor to ceiling. So instead of having, 85, 90 degrees in the ceiling and 68 on the floor, you got almost an even temperature within the envelope that's going on, like you can see in the slide that we have here. And one of the things I wanted to address in the slide here real quick, because it's a misconception we get hit with a lot. And I was actually talking to April at the very beginning of the class today, and there's a big misconception that, like down in Florida, we'll address Florida because it's great. People are like, wow, you're selling destratification fans in Florida. Why do they need that? You don't want to bring that heat down. They're going to be uncomfortable with that. That's not exactly how the fans work. It's a misconception. First of all, our fans don't produce any heat. They're just fans. So you're not producing any heat that's going to heat that space. You are going to bring the heat down initially, but it's going to blend with that space, and with that air column that comes down with our fans, it's going to consistently blend that air, keep the air circulating within that space so you have an equalized space that's going on there, whether it's up here in Milwaukee or whether it's in Orlando. Next slide. And here's some of the applications that our fans have gone in: athletic facilities, aviation, bars and breweries, pools, manufacturing, greenhouses, grocery stores, all these ones that are listed here that you see we've got our fans in. literally almost every single one that's right here, I've sold fans in that are in these applications here, that we're looking at. So if you have, one thing I would say is if you've got a project that's going on and you're curious, hey, is this one going to be ideal for a destratification fan? Just ask. Because generally I haven't run into one usually where they're not necessarily going to work where I say, nah, it's not really going to be a good fit. Occasionally there is, but most of the time I'd say 95% we're going to be able to go in there. We even get clients from the Caribbean and South America that are saying, hey, we need your fans, so destratification doesn't really matter where your environment is. Destratification is going to work most of the time. So a lot of these applications will kind of show that. Like for instance, the bars and breweries and greenhouses and grocery stores are three areas that seem to be really on the uptick right now, as far as requests for fans, requests for information. Good friend of mine back in Colorado, where I'm from, actually has a distillery. And I was getting tired of actually going in there and wearing my coat every night for the entire time that I was there. And I was like, look, you know what I do? You know what I do for a living? You got to put my fans in here. Now everybody goes in there and they can take their coats off during the winter and it's a lot more comfortable. And I said, your clients are going to stay. They're going to order more drinks if they're here longer because, they're going to be more comfortable. So that goes back to that earlier slide about, occupants being comfortable in there. It's not just the workers, but it can also be customers that are coming into something like a bar or a brewery. Okay, next slide. Energy savings. The energy savings listed here are not actually from our company. These are from clients that have reported to us. So we've got heating costs fall by 20 to 50, cooling costs by 20 to 40, return on investment 12 to 24 months. These are clients that have actually come to us and said, hey, this is what we're seeing. And we're like, wow, so this is impressive. These are different things that they have told us. The cooling costs fall by 20 to 40% is an interesting one. That one I have up there because that actually comes from Australia. When I was talking to April earlier, she had actually asked me the question, are your destratification fans seasonal? Do you see, a downturn in seasons and an uptick in different ones? Well, originally 5 years ago when I came in, it was during the winter time. You'd see a big increase, and in the summer you'd see it drop off. To some extent, it still does a little bit, but really what it comes down to is just educating and saying, hey, these can be used all year round. And what happened in Australia has their rooftop units cost about 3 times the cost of the ones here in the US. And so what they do is they look for alternative cooling down there. And what they do is they look for evaporative cooling through fans. And so what they do is they'll go into a particular project. They're like, hey, we can't afford the rooftop units. What can you do? So our branch that's in Sydney will go in and talk to them by that. And this is kind of some of the reports that they're coming back from Australia, talking about their cooling costs falling by 20 to 40% by what they're doing down there. So it's kind of interesting. We're trying to get some white papers actually coming from Australia in the next few months. So we can have some more data from that. So we're kind of waiting for information to see what they're doing there with that. But it is kind of nice to see that for cooling effect that you can also use the fans there. They're not just for destratification. Okay, next slide. Here's something that did come from an Airius study. We wanted to have third-party collateral is always huge. If you can get another company to come in and speak for you and do some testing for you, it's always great. This was the Building Scientific Research Information Association in the UK. Did a study of our fans at different ceiling heights, different delta T's, and came up with an average. You'll see the square up to the top, off to the middle right a little bit, where it shows an average savings of about 26.3. And that's what we list. When we put out there about the savings for basically the heating and destratification, because destratification is still number one for us. That's the main savings that we typically get, because if you've got a equalized temperature within that thermal envelope, you can set that thermostat back. Anytime you set back a thermostat, you're going to save energy. It's just going to happen. And so this is a study that they did for us a few years ago and actually came up with this data. And we can provide this. I have this information where I can send out if anybody wants to see this.
Okay, so this is independent of fuel costs. This is just as a percentage.
Yeah, correct.
Okay. So what you're highlighting there is at a 33-foot ceiling, you're saving about a quarter of the whatever the utility is, just one over the other.
Right, and we go off that 33-foot ceiling because that's about an average. 33 foot is fairly common. A lot of you guys that have gone out there and spec the fans and that type of thing, 30, on average, about a 30-foot ceiling is fairly common. That's that's one typical of a lot of the different projects that are out there. So that's kind of where we, base that on to, when we talk about energy savings and that type of thing.
Actually, if you go back one slide,
Yeah.
sorry. The delta T between the ceiling and the floor on a 33-foot ceiling, I would expect to be higher than 14.4. So this could actually be a little bit understated.
Yeah, we're a little bit conservative on it, just to be on the safe side.
Usually think a degree a foot. So,
Yeah.
33 feet out of the occupied zone should get 23 degrees, not 14. So yeah, this is conservative, it seems like to me.
Yeah, it could be a little bit higher. They, did that on purpose, just to be a little bit conservative, but because it's always nice if it ends up being a little bit higher than what you expected. So that type of things. I wanted to talk a little bit about air purification because this is also another hugely growing area in our fans, especially since 2020 for obvious reasons. Air purification was something we always had available, I'd say over the last 10 years, but that's really expanded since 2020. Everything from reducing the amount of dust and pollen in the air to deactivating viruses. And we brought in, basically started in 2020, what we classified as our Pure Air line. And with the Pure Air line of fans that we have, basically do it two different ways. We do the UV light that has the UV cell in it, like you'll see pictured here from Guardian Aire, or like the Guardian Aire that we've got from RGF. And then we also do the ionizers that come from GPS. So we're going to look a little bit about that as we go further into this, and then talk about a little bit about what they do, reducing emissions, reducing condensation. We're going to, as we go further into the presentation, we're going to talk a little bit more about that. Comfort, we already talked a little bit about that. More comfortable working environment, also more comfortable for customers if it's something like like a bar or a distillery, brewery, that type of thing. Especially since though Colorado is very similar to the Milwaukee area, and we have a lot of breweries. It's very big in Colorado. So we've got a lot of clients out there that have that type of an environment. So they want to make sure in the cold weather and the hot weather that they're going to be comfortable. So very much a growing industry. Also increase workers' focus and productivity with the Pure Air line that we've got. Also reduces absenteeism because you don't have as many sick employees as well. We'll be looking at that. Understanding the technology, what kind of sets us apart, Tom talked a little bit earlier at the very beginning about how we had come out with this type of destratification fan, and there's been some competitors that have come in since. What really sets us apart from that type of destratification is our patented stator and our tapered nozzle design, because what that does is it controls the air column. Makes it different. So once you have that controlled air column, you can actually set that up to design a system of fans for a particular space to have that air column go down. So basically what we can look at that point is say, hey, this fan covers X amount of square footage. Like say, for instance, we've got an Aire Pair Model 25. Each fan covers 1,200 square feet of destratification. Based on that, and then an 18 to 28 foot ceiling, based on those two figures right there, then you can start designing a series of fans that's going to go in for that space. At least it gives you a good starting point to where we can look at for that. And the stator, again, within the fan helps control that airflow so that it basically that air column goes down, hits the floor, comes back up, and then continues to recirculate. And since the patented stator is out there, none of the other competitors have that stator. So really their air columns are not complete. You'll find we get a lot of complaints from clients who tried other ones. They come back and like, their air columns don't work, or they don't work like we expected them to do. And that we like the idea of your fans. We've seen the smoke tests that you've done on YouTube, and how they work. So they go with the fan based on these types of designs. And this design came on early on. The owner of our company actually designed the fans for our own need. That's where the fans came from originally. We had in our own manufacturing plant, we had excessive energy bills. I mean, they were just incredible. And he designed a prototype. Ray Avedon, our owner, designed a prototype that he put in our manufacturing floor, put several of them up. And lo and behold, our energy bills dropped enough that public service came in and actually said, hey, are you going out of business? Your energy consumption has dropped so much, something's going on, you know, and they're like, no, we didn't. We just designed a product that's helping us save energy, and we knew we had something. So from that point on, we started marketing to different clients, originally started in manufacturing clients, that type of thing, that were similar to us, and then expanded from there. Next slide. This is a question we get all the time, especially at trade shows, different things like that. Airius fans versus the HVLS fans that are out there. And because there's going to be certain situations where HVLS fans are going to be, you know, better in an application than maybe ours are for whatever that is. But then there's going to be other ones where they're going to be able to be used together, or ones where ours are definitely going to be above what it is that they're going to be looking at. And that's what we've got here. Because you're looking at, in comparison, hidden blades. That's going to come in great when you're looking at basketball courts, volleyball courts. You don't want an HVLS fan in that, because you don't want to have ball strike going on and with fans that have blades on them. That's not going to be conducive to safety. So our fans are going to work very well with that. Unobstructive. They blend into ceiling features very, very well. Lowest cost up front. Our fans, when you're putting them in, you're looking at basically dealing with single phase power instead of 3-phase. You're not looking at ceiling modifications, that type of thing. They basically are a small footprint that goes up into the ceiling and blends in architecturally as well. So it works out very well. Running costs. This is something I love talking to people about. Our product started out as a green energy saving product before that was even something that people were really talking a lot about. Most of our fans, basically the wattage that they run go from anywhere from about 35 watts up to the highest of our fans, about 90 watts. So you're looking at a light bulb, basically, is the energy that's being used. So very, very energy saving devices. No strobing effects that are going on with the lights, which is another nice feature of that. No height restrictions, which is great. We don't have to deal with that. Replacement warranties, 3-year warranty standard has been working really, really great with that. Low noise. Most of our fans, you get a very, very quiet sounding fan that comes from those as well. So all great, points to compare with the HVLS fans. Again, we'll talk about a little bit about opportunities to look for. Again, that large differentials between the ceiling and floor. We talked a little bit about that. The high bay spaces, here's a good illustration of what that is, what high bay spaces look like when you have a warehouse like is pictured right here. High supply returns that we've got going on here is a good example of that as well in this location. And then here we have Ron Swanson. This is me in Colorado every winter. Please turn the thermostat up to 90 and leave me alone. As I've gotten older, cold bothers me just dramatically. So poor thermostat location and minimal air movement just really do a number on a building, causing energy costs to increase, comfort level to drop. It just causes a lot of problems with that. So in looking at that, destratification fans can come in and help deal with that situation and help make that area a lot more comfortable. Sweating slab syndrome is another one. I think the only area I deal with that doesn't deal with humidity is where I come from, Colorado. That's the only dry area really that I deal with. Everywhere else that I have as a territory has humidity. And sweating slab syndrome is something that they deal with in Florida, something they deal with up here. And basically, you've got the temperature changes from night to daytime. In warehouses, you get that, and it causes safety issues because you've got guys slipping on the floors. And I also found out in talking to a few gentlemen in some different projects that so many buildings are going up, so many warehouses and things are going up so quickly. Amazon's a prime example. were until they put a stop to them, but they were putting up warehouses so quickly, they weren't letting the concrete cure correctly, which even enhances the sweating slab syndrome even more. An HVLS fan will not bring an air column down to the concrete floor enough to alleviate that. So a destratification fan works really, really well to do that. We got approached about 7 years ago by FedEx in Fort Mill, South Carolina. And they said, hey, we've had several of our guys get injured slipping on the floor. We tried HVLS fans, they didn't work. We want to give yours a shot. So we came in, put in a series of about 20 fans, it alleviated it within a day, which was incredible. Enough that they came back and they said, hey, St. Petersburg, Florida and Ocala, Florida also want the fans. So we went down to Florida. At that time, that was right before I came to the company. So my friend Taylor Horowitz went down to that location, those two locations for FedEx, put those in and alleviated that as well. And that's been working really, really well. I actually, in November, was doing a presentation in Charlotte, North Carolina. And one of the guys in the audience, his father worked at that Fort Mill location and said it's absolutely true. He turned around and spoke to everybody in the crowd and said they did put those fans in there. My dad was right there. He kept speaking about how that alleviated those accidents. So that was kind of a neat coincidence to have happen, but it does. It really helps with that situation. So if you're talking to somebody in a warehouse about destratification, this is another good point to talk to them about as well. Next one. In the last presentation, when Joe was up here, he talked a little bit about the FLIR going in there, talking about infiltration, showing that. This is just another example, where you get where you get that type of situation going on in a building. This can kind of help get in there, help alleviate some of that as well. We're going to talk a little bit about the fans themselves. The AirPair series was our first series that we came out with. That's kind of been our bread and butter for a number of years. The unique design that we've got, again, we talked about the stator and the tapered nozzle. Get a lot of questions about, hey, can we angle these? There are certain projects where the fans may need to be angled. Natatoriums are a good example of that, where maybe you want to put them around the perimeter of the pool to blow the chemicals of the pool off the surface of it. I've talked to a lot of clients who have kids who swim, and they said it actually can cause swimmer's lung breathing in that chemicals. It can cause lung damage. So in natatoriums, you're going in, you can put the fans to take that chemicals off the surface of the pool, help that be healthier. In fact, that was first project I ever did with Airius was a natatorium for Carson Newman University in Tennessee. And that's exactly what they did. And since the bail handles are ratcheted, you can angle those, so you can do that. So you don't always necessarily need to be straight down. I've really, over the last year, it's been getting kind of crazy. I had right before I had a territory change, I used to have Louisiana, and I had a fitness center that had so much humidity in their ceiling. They took the fans and pointed them up to alleviate the humidity in the ceiling, and it actually worked. They put four fans, faced them up to get rid of, they had so much humidity in Baton Rouge, it was actually dripping. And they said, hey, we want to try it. We tried everything else, nothing is working. So they gave that a shot. It actually did very, very well. So going in there, it's kind of crazy, some of the applications you can do with the fans. The seismic leash is another one I'll highlight. I actually sold a project last week based on just that, just the seismic anchor that we've got right here. The main reason was that a competitor of ours had gone in there, talked to them. They did not have a secondary way of keeping the fan in the ceiling. Their local code required them to have that. So that's another high point too, is check the local codes and see if they have to have a secondary way of mounting the fan in the ceiling. The competitor did not have that. They lost out on that because we did. So that's an important point on that as well. And another important point about that is the seismic leash must be installed with the fan. It keeps the fan from moving as well. So it's installed at a 45-degree angle, helps stabilize the fan, keeps it where it's supposed to be. But it's also nice to have that up there as a safety feature. We don't really have the fan, with that bail handle, it's very solid, very well made. They don't really come out of the fan, out of the ceiling or anything, but it's nice to have that secondary safety feature there as well. Ultra quiet, we're going to talk about some of our fans and talk about what makes them quieter. The Pabst EBM motors that are in them are already for the most part quiet, but we've got some that are even quieter that were designed specifically. Yeah, Tom.
You just got like 5 minutes.
Okay, we'll go to the next one here. We'll speed through them. Pearl series, this is our contractor's grade one, primarily just for grocery stores. The designer series, this is one for architecturally specific spaces. These can be painted. If we have the Sherwin-Williams number, we can paint these in the factory so they can be matched up. It goes all the way up to 125 feet, like in athletic training centers, so and event centers. Next one. Onyx series is a new one with the side entrainment. This is our most popular fan recently for warehouses, gymnasiums, that type of thing. Higher velocities are available there and large coverage, 15 to 50 feet. So just if you've got anything within that space, an Onyx is probably going to work for you in that space, and they run very quiet. Next one. Q series is our quietest fan, so it's great for sound stages, worship facilities, libraries, that type of thing. So if you have something that's extremely sound sensitive, it's a great way to go with the Q series on that. Retail series, this is a narrow aisle, and it's an R20. Primarily, you'll see this mainly in grocery stores where they're just looking to do aisles and that type of thing. Don't do too much more with those other than grocery stores. Excellent. Suspended ceiling, this is again, HVLS fans really don't work well in a suspended ceiling. So if you've got a drop ceiling, offices, classrooms, this does really well. And then the Pure Air series, this is the again with the ultraviolet and the ionizer. The ionizer that we have does not produce any ozone whatsoever. So if you've got an ozone situation where they can't have that, they are rated UL, trying to remember the UL rating on that offhand, 867. With that UL rating, they're able to go into school. So we put them, in fact, I just got done with a project at Alabama A&M where they put all the ionizers in their classrooms that they have existing, $250,000. So they didn't want to mess around. They wanted to get going with this to take care of having students come back to class, come back safe, deactivating viruses, that type of thing. Reduce absenteeism. So that's done very well with those. Bismarck School District, that was the first school related project I did with those, and they've done very well with them. They can go in both the regular free hanging, the Onyx, or the suspended ceiling. We can put those ionizers in all of those. And again, those are made by GPS. Next. Again, real quick, the shaded pole motors are basic ones, the shaded pole and permanent split capacitor. Got the series of triacs that we've got going there that go with that. Most of you guys here at Airflow know about those already. We dealt with those for several years. Next one. The electrically commutated motors, basically set up to go in a 0 to 10 VDC signal back into the building automation system or BACnet. We're not doing so much with the BACnet 4 and 8 now. Primarily the BAC 24 is the way to go on that. This is all on our website on that. So basically, we've got a lot of that going on with the integration back to the MSTP IP panels with those, so we can set those up. So if you have a BACnet requirement on that, we can take care of that. This is coming up new. I wanted to make sure and get this in before the end of the presentation. This is our Delta T fan control. Late spring, early summer, we'll have this out. We're going to have this available in both on the shaded pole and the EC motor side. Basically to take care of it through doing sensors and an LED display on this. It's if you have a situation where you're wanting to run the fans and maybe have something a little quieter than a triac, this will give you a way to go there. But also we can do this type of control if the spec is calling for it with the EC motors as well. So stay tuned for this. It is on our website. So if you want to jump on our website, look under the products under Delta T for the controls. You can read a little bit more on that. It's just currently in production right now. So I just wanted to give kind of a little early preview on what's coming for a little bit later this year as well. All right, and that kind of wraps it up there. So hopefully that kind of came in with the timing there pretty well for you.
I just wanted to comment a couple of things. I don't know if you and I talked about it, if maybe it was Robert, but one of the things that it seems to me, since this is a thermal equalizer, is can you just, instead of you had a slide where you had a lot of spiral duct and sidewall grills.
Mhm.
Have you been successful eliminating ductwork?
Yeah, one project specifically comes to mind is the Colorado University indoor training facility. They came to us 7 years ago and they said, hey, they're coming to us saying, hey, we need, they're a school, it's a university like any other school, they're on a budget. They're like, we can't afford to put 2 more rooftop units in and all the ductwork that's gonna go along with that. So they came to us and they said, hey, we wanna look at putting your fans in there. We went in with our model 125s and we mounted them at 90 feet. So I mean, this is a very, very tall facility. And we're able to reduce their material that they were looking at having to do originally by thousands of dollars. I actually checked in with them a couple of years ago. They actually came to a trade show, some guys that were part of that particular project, and I asked them how that was going, and they said very well. Not only was it going very well for them, they've actually talked to other universities about that and send referrals on, which has also been working as well. So again, that third party collateral, having a client go out and talk for you and say, hey, this has been amazing for us, is just phenomenal. They actually spoke to the new, I don't know if any of you have been to Las Vegas lately. They've got a new event center out there. I can't remember the name of it. It's a great big dome they have out there. Same thing there. They came to us for that particular event center and they said, hey, we want to reduce the material we're needing to do this. And we heard about Colorado University. Can you do that here? Same application. We went in and did the same thing with those guys as well. And so, yeah, it's huge. Material reduction is a big thing, especially if somebody is on a budget. So if you're talking to schools or that type of thing where they've got that going on, that's a great thing to talk to them. So I'm glad you brought that up, Tom.
And for those of you who have architects who like cloud ceilings, this is the Band-Aid you put in after you realize that you have a 15-foot ceiling and not a 10-foot ceiling. So that's a little challenge too. All right, how about a nice hand for David? Thank you very much. And I think we're going to turn it over to Brent Fullerton, remote from Springfield, Missouri. We're going to go right into the some details about selecting large fans.
How y'all doing? Actually, I am remote from spring break. So let me try to reshare this again. And we're going to go. Is it coming through?
Yes. Oh,
Very
no.
good. Okay.
Brent, 1 second.
It's coming through on.
Coming through in the, Brent, could you email your presentation to events at Airflow?
I cannot right now. I can possibly later in the day.
Okay.
It's about a 200 meg prezo, believe it or not. So I can try that. If not, we'll get it accomplished next week when I return from spring break.
Okay.
All right. And you'll get the slides next week as well. I know Tom had some last week, so we'll go from there. Okay. So following the topic that we had already set out today, and also stepping upon how Tom actually started this morning, a lot of these different products actually can work hand in hand. And so I'm going to go in and bring that in from the standpoint of roof mounted fans, specifically from the fan industry, from the Cook side. I love this slide that Tom did actually for our webinars from last month, because I know a lot of folks, particularly from the design build in and even the consulting in, and myself being a former consultant, can get in a rut from the standpoint of, we're going to have this large building, we're always going to use this exact style of fan and that type of thing. And I'm going to challenge those of you that are on this to think a little bit outside of the box and also give you some tools to go from there. Now, in the interest of time, we're going to go over just at a 30,000 foot level some of the things that we touched on very in depth last month in the seminars. First off, belt drive versus direct drive. Okay, there are pros and cons of each. Neither one is mutually exclusive. They can be one better than the other based upon the way that they're installed, as in and access to that, or also the service crew, the owner, the facility maintenance, that type of thing from the standpoint. So a belt drive, of course, it has a motor, it has belts, it has shivs, it has that method of transferring the energy from the motor to the fan shaft to go from there, where a direct drive has the motor coupled directly to the rotating device. So the other thing that we're going to hit on very carefully and very briefly is fan performance characteristics. And here's the reason I bring that up. Of course, we have the Aire handbook and the fans chapter out of that. We also have the engineering cookbook, and I believe there should be some for handouts there with the folks that are in actually in the training center. Not, we can get some more. But knowing the different styles of fans, while they can all be roof mounted, some are more appropriate for different types of exhaust, different types of systems, or different types of supply. So let's dive into large roof fans and specifically the exhaust types. So our online software, you can go in and make a lot of selections right there. In the upper left-hand, roof exhaust is number one. You can input your CFM and static pressure. In this case, I've done 17.5 at a half an inch because that seems to be a very often go-to range depending upon the size of the building that you might have. So you can get a wide range of products that come up. In this case, I'm narrowing it down to 2 different typical styles of products, but here is some of the different models that could be utilized. And you could run them all side by side and take a look at it. Now, yes, there's a big alphabet soup, so we're not going to hit on that, but I'm going to show you different styles up close. And being the spun power roof ventilator, different parts, different folks like to use the down blast. Some folks like to use the up blast. So from that standpoint, the up blast style does create less turns in the airflow. So it uses less energy. Depending upon your CFM and static, it can use significantly less energy. Additionally, it does cost more because there is more material. So going right in here, and as I always like to refer to it, pulling the lever on the slot machine after you dropped your coins in, you've got your CFM and static pressure, and you've got those selections right up there in the wide range. So you can see both styles, the down blast style and the up blast style. Now you can see the relative costs, you can see the budget price, but you can also see the brake horsepower and even the sound. Let's look at this a little bit closer. So for the same size fan, one versus the other, we can look at this. And then we also have something that's called an annual energy cost estimate calculator. You can either use ours or you can use a very simplified spreadsheet. Now I did dive in and get your local utility rate, and that's a little over 12 cents per kW for an industrial user. And if you look at the brake horsepower, while it's not monumental difference, it does add up to a difference of $500 per year of energy savings if you use the up blast versus down blast. So diving in a little bit deeper. So yes, it does cost approximately $800 more, but you're saving approximately $300 per year. So easily below a 3-year payback. Once again, I'm trying to show a lot of tools that some folks are familiar with, other folks are not. Also different styles of products because some are applicable to the systems you may have, some are not. But most importantly, I'm trying to give you the tools to really dive in to do the energy comparison and the best product from day one. Not that either one couldn't do the job, but we all like to get the most bang for the buck. I have some design build contractors. I have some consulting firms across my entire region that they always go immediately to the first style fan up on the left. I've got some that'll always go to the lower one. And I've got some that have a mixture of different styles of product. So let's continue this. What's this one? Well, this one has the same interior guts as those two prior ones, but it has a larger hood on it. It does direct the air down. And if it doesn't matter that the air is being directed down, but you have a larger hood, it has less pressure. So we're going to run that selection back through that exact same CFM and static pressure. And what you'll see right off the bat, when we go in here, you've got a significant energy savings right off the bat. And looking at that, so for only a $400 increase in first cost, you're saving over nearly $630 per year. So you've made up the difference in price of the product. Once again, I'm trying to show different products, different styles, as well as the tools to make a full-blown evaluation. Now, this is a large go-to type product. Notice it has a prop inside. On this particular one, it's belt drive. We also offer it in direct drive. But this particular product, in certain parts of the country, certain design build firms, certain consultants, this becomes their number one go-to style of product. And we'll dive in and look at some of these different prop styles of products and look at it from there. Now, here's the grid, but let's dive in and look at it a little closer. So where we had the large scale power roof ventilator versus the prop, you'll notice that you dropped your brake horsepower significantly and quite a bit of energy savings. So in this case, you have a first cost savings of your purchased product of $400, but you also have an annual energy savings of over $400 per year. The other thing, and the reason why a lot of design build contractors do like to go to this style product, is the method that it can arrive to a job site. So your shipping costs go down. Your ease of installation is there as well. It takes a lot less time to get these installed. So where we were first looking at just the first cost of a product or the first cost and the energy use of the product, now we're starting to look at first cost of a product, energy use of a product, as well as first cost installation of a product. So all this starts to build in together to help look at the overall picture of those, what is the best product for your specific application or building. Direct drive, as I mentioned, goes from there, and you can have a lot of range of selections on there. Now, one of the other types of products that is often used is still a prop, but it's a butterfly damper style product. Now, the butterfly damper style product has its pros and cons. This can be used as a smoke control, just as your power roof ventilator upblast could. But the drawback is you do have a hole through the roof. So a lot of folks will put drain pans suspended from the ceiling and everything else, because your outlet velocity from a product in certain storms is not high enough to overcome the driving factor. Additionally, if you have a pressure differential go through because of a storm or wind or anything along those lines, the path of least resistance to get the pressure equalized in a building can come into play. So the butterfly dampers, even if they have magnetic latches trying to hold that down, it can pop those things open. Now they'll come back down once the pressure is equalized, or they can shatter. But this is one of the most frequently cons of this style of product, but they are very, very cost-effective styles of products as well. The other thing is, notice the style on the left, you can service it from inside the building, where the product on the right has to be serviced from the exterior part of the building. So looking at several of these styles of products, we go in, we can zero in versus one style of this style, but normally, then we get into the point of using a backdraft damper. Now, a backdraft damper is impossible to be used on this style of product on the left without a lot of difficulty, because then you couldn't get in to service the product from below. So I'm going to reselect this, taking a pressure out, because these are normally non-ducted and also are not installed with a backdraft damper. So now you get a lot more options. So once again, then you start looking at the different aspects of your specific system. So this is an old school style of product. We sell a bunch of them every year. They have been a go-to for years. It allows for service of the product on the roof. It gives a little bit of height. It can be used with a backdraft damper down below if you wish. But from that aspect, it's more of a legacy style of product. It does have more first cost. It does have more installation costs, but they're tried and true, and we go from there. Now let's go back and look at some more different styles of products. Once again, we're still in the exhaust mode. So taking a look at all of these legacy styles worth of products, we can get a wide range of selection, whether belt drive or direct drive. Now, when they're direct drive, the motor cannot be easily serviced from outside the roof. You have to actually take the product off the roof curb, or you have to get like a cherry picker from below. So once again, there are pros to a belt-driven fan. There are pros to a direct-driven fan. Likewise, there are cons to each style of product. So wide range. Now, let's talk a little bit about roof supply fans, very, very briefly. Now, wide range of supply fans, you can have some that look pretty, you can have some that look boxy, you can have that. Now, all of these styles, now, while they can be reversible, they can be supplied with filters, these are non-tempered style of fans. Once again, looks just like what you saw earlier, except in this case, the airflow direction is supplying air into the building. Once and filtered, as I mentioned. Now let's look at some specialty designs and where these really come into play. And airflow has been utilized this product through the years. We saw a lot of these for some specific applications. It was nicknamed an economizer fan years ago, but it allows 4 modes of operation. So it can mix the outside air with the inside air. It can strictly recirculate, or it can supply outside air, or it could exhaust outside air. So this one product can do these different operation modes. So it has some very wide range of opportunities for that. Then also the hooded series that you saw earlier for serviceability, it can be mounted on what is known as basically a tall curb with an access point, and you can get in and service everything from the roof area, which works wonderfully if you have a flat roof. However, if you have a sloped roof, that can be one of the items to consider when you're choosing which style of fan. So if you notice right here with this drawing, you can see how you can get in through the access points. You can actually even pull the damper out through the sides. You're not having to get in from below, particularly beneficial if you have an extremely tall roof. Now, not doing a super deep dive on controls. We did that last month, but I do want to highlight a couple of controls where these come into play. So for the Veriflow, which is the EC and PM style motors, we offer, as well as for regular belt driven fans, we offer a control method, but here's where it comes into play. In the old days, you had the option of simply a 2-speed motor, which would be a 50% split on the speed, so a high speed or half the speed, or you could have a 1/3, 2/3 split. So it would split the fan speed, and you would have to have either a switch or another type of control. That was the old days. That was back in the days when I still had hair. Now, very easily, there's simplified controls. You can set whatever you want for the high, whatever you want for the low. And that can be controlled not only by a switch, but it can also be controlled by a control. So what if you wanted to set a temperature range at which it kicks to a higher speed to exhaust more air? Or what if your humidity gets high and you want to tie into that? Now, it can be a standalone or it can tie into a building management system from that standpoint. So all of that are options for controls. Like I said, we did more of a deep dive about last month. I don't want to recreate the wheel, but I do want to highlight and pull that back in. Now, there are also some specialty applications that can affect the choices of the style of product and the type of product for these roof-mounted fans, specifically power ventilator for smoke control. Some codes, some building designs require, in case you do have a fire, a method to exhaust the smoke. And there is a specific UL outline and investigation for the product. And with that in mind, that ranges. And here's a simplified outline of some of these different style of products, but some of those roof mounted products, just like as we highlighted, you can see right here, they have that option. Now, in some cases, you have to have all of them listed. Some cases you don't. Sometimes you only have to have some. And I'll allow you to do that deep dive on your own or with our team from Airflow on your specific buildings and designs, but I want you to be aware of that. And so that goes into a little bit more detail on that history. Pre-1990, there were a lot of regional codes that came up, were here and there, and that caused a lot of grief and heartache, not only for the consultant, also the design build contractor, and even some code officials, and definitely for the manufacturers and the representatives. So this came about to be a level document that pulled a lot of different sources. So roof mounted, inline, all that. Once again, we did a little bit more of a deep dive on that last month. Once again, the software will go back and allow you to, over on this side, smoke control, make selections. And this is our installed version of the software, and you can see these selections from there. So what I did, basically in the interest of time and trying to keep to the time frame that we had, is I came up with a sample design checklist. And once again, you'll have this here sometime next week when I return to the office. But some of the primary things just to kick off the design scope. First off, the airflow requirements and direction of flow. Well, you've heard it from some of the other speakers today. What are your required air changes? And also, what's the direction of flow? Is it exhaust? Is it supply? If it's supplied, is it filtered? Does it have to be filtered? Can it be non-filtered? Can it be heated? Can it be cooled? What about reversible applications? There's a lot of time that reversible applications are very, very beneficial. Or what if you want to have a mixed and recirculation mode? The next item after that, any project special application requirements, if any. Smoke control, I went over that. I did not go into detail on minimum outlet velocity requirements. We did some of that last month, but sometimes you have to exhaust things out of a large building, some different systems, and you have to have it at a outlet velocity high enough so that you don't have to worry about it coming back in, and that would normally be an emergency situation. What about if you have airflow temperature? And when I say airflow temperature, what I'm referring to is, what if there's a lot of heat in the building? What if there's a process? Some of the products actually have to be modified to handle that airflow temperature. Also, old school method, I used it a lot and I still see it used a lot. What if you just want to remove heat out of some of the systems? We do a little bit of that in the engineering cookbook. Go in there. There's some delta T methods to reduce some temperature in an area. Then also, one of the things to be thinking about is your overall project serviceability, access and facility maintenance. I hit on that a little bit when I said the pros and cons of a belt drive versus a direct drive, but also in the style of the product. Where can you service it? Is it a flat roof? Is it a highly sloped roof? So all those things filter in. And once again, we're trying to go through and zero in on what's the absolute best style of product, the best performance characteristic for that. And any other project controls that you might have, requirements you might have, if any. So temperature control or 2-speed requirements or building control integration. Once again, I simplified this down to kind of a checklist to go in from that standpoint, but hopefully it's a template to go in there, because there's a lot of different styles of fans that can be used and are used literally every day, and go from there. So with that, I think I was 2 minutes over, Tom.
Can you hear me?
Yes.
I can.
Brent, thanks so much for doing this remotely and interrupting your spring break for us. So how about a nice hand for Brent? Right. With that, we're almost caught up. So thanks for being so quick. We're going to start back with Powered Aire in about at 11:15, and we'll be right on time. So thanks, everybody.
Thanks.
That's more than fun. I have any idea. What?
It's right out here, but it literally like, it's like, I would have to sit some car back.
Go
So,
to the air curtains, turn down. And then go back to Zoom before you put start sharing.
That's Thursday.
Go to the Zoom webinar.
Unless it's more than one day, but I know
thought
that
it
it was
was
more than one day.
Going on Thursday.
Oh, is it?
Maybe like some day.
No,
But it's today. Sound sure, so you're good, and then go.
Oh. Now we'll see him fight.
Everybody, welcome back. Our last third and final segment, we've got Powered Aire speaking, and then followed up by AbsolutAire with a little demo. But Jamie, we're
working together for what? Well, we won't say how many years, but just more than a
Half
couple.
of my life.
More than a couple. And so, I really, pushed the point with Jamie, you know, one of the first things that seems to get beat out is air curtains. Code in some instances requires air curtains, but not all that much. And so I'm really asked Jamie to push you guys and say, this is a compelling case for energy saving, and that's, you know, one of the big themes of this presentation. So she's gonna hit you with both barrels, and I encourage you guys to consider air curtains for your open doors, to really try to stick to your guns, because she's gonna make a great case for keeping them in the project. I think, you know, we didn't always have makeup air, we didn't always have Destrat, or we had little paddle fans. I mean, we're all evolving. This is, you know, this is kind of one of the last ones that really needs to be implemented for protecting our buildings and keeping energies inside the building. So without further ado, Jamie.
Sound.
All right.
Thank you guys very much for having me today. I really appreciate this. I'm just going to talk about air curtains in general, benefits, like Tom said, energy savings. Also, something I'm really going to touch on is vestibule accession. One thing that has really pushed air curtains along is now you can use air curtains instead of vestibule, which saves a ton of money in upfront construction costs. Basic concept, I'm sure you guys know what an air curtain is. It's just a wall of air separating two environments, whether it's hot from cold, clean from dirty, flying insects to non-flying insects, even smoking from non-smoking. It is just an invisible wall of air separating two environments. Things I'm going to touch on today, one, like Tom said, energy cost savings. Most people don't realize that when properly applied, you are going to see less than a 2-year payback on the equipment when using an air curtain. Increasing comfort, employee comfort, customer comfort. Also, sanitation is a huge benefit of air curtains, flies, bacteria, safety, better building design. That is the vestibule exception I was talking about. And then I'm going to close with proper selection. It's great to use an air curtain, but if you do not properly select an air curtain, I have some engineers that are really comfortable with one model, and they'll use that model on a drive-through window and also a 12 by 12 dock door. And I can assure you, you're going to need two very different models for different applications. Just a general quick synopsis. I don't know if you guys would work mainly in this area or if you kind of branch out all over the country, but here's a general quick look at what you're going to see for a specific application for cost savings. What I'm assuming here is an entry door, 6 foot wide. I believe it's a 6 by 7 foot high standard opening. Let's say you're dealing with a convenience store is what we're working with here. Standard 6 foot wide by 7 foot high opening. Inside design temperature, 70 degrees. Hours per day that entry door would be open about 4 hours, 7 a.m. to 11 p.m. and that's 7 days a week. Just with that data, and most manufacturers are going to have some form of savings calculator. I will get into ours here in a minute. If you plug that data in, it's going to show you, and this is just for heating season. One heating season, the savings you're going to save per one heating season. Chicago, $6,500, Bismarck, almost $7,500. An estimated delivered cost for a unit for this opening, if you're looking at unheated, maybe $3,000. If you're looking to add heat, maybe $3,500. So in this instance, less than a year payback on most locations on the equipment itself. Now, if you wanted to get into something more specific for this particular area, next slide is, this is our particular cost savings. If you were to go to our website, go to tools, we have an energy cost savings. This is what you would need to fill out. The application, is it heating or cooling? You are going to see savings for both. Obviously, in this environment, you're going to see a much more significant savings during heating season, but you can run them both to get a total savings for a year. Inside design temp, again, the things we just went through. Now you're going to see here, there's a place where you need the model. Also on the website, you'll see a product selector. So you enter the application, your door dimensions, if you want heat, it's going to give you the product that we would recommend. So it's very easy to plug it into this right here. Getting down to the state, the city, door coefficient, that's kind of a standard. You can change that if you want to. And then again, the electricity and gas costs, you can enter whatever is applicable for your area. So I did a specific one for a commercial and also an industrial application. This is the commercial, kind of the same scenario we were dealing with before. Maybe a gas station, retail facility, inside design temp 71. Lower the hours per day to 3, 7 a.m. to 11 p.m., 7 days a week, 8 foot wide by 6 foot high. The model I selected, we have a CED. And I'll touch on noise in a little bit. I know When we talk about air curtains, a lot of people think of these like big, loud jet engine things that mess up women's hair when they walk underneath. We do have a commercial line of air curtain, this being one of them. It's called a customer entrance door. It's the quietest air curtain you're gonna run into. I think it's 53 dBA on high speed, which is a normal conversation level. So we have a special plenum design, which I'll touch on. It makes them a lot quieter than what you might associate normal air curtains with. So this is the information you would plug in. It will give you the annual cost savings. Again, this is just for one heating season is $4,600. So less than a year payback on the equipment. If you go to the next slide, since I'm just a salesperson, I can just throw numbers out there. If you print out this formula, it's going to give you a 3-page printout backing up all of the documentation. Up top, it's just the data entered from the catalog. Coming down, you're going to see the climatological information. Again, this is just one heating season, so we're assuming November to March. Average high, average low, average wind speed. This all comes from NOAA. The second page is breaking it down into the average temperature throughout the operating day. Third page is probably what most engineers would be concerned with. It's the actual equations. As you can see, well, you probably can't see, it's very small, but I'd be more than happy to email this to you if you want, or you can even play around on the website and you'll see it pretty clear. Everything's documented from Aire. It's taking out it's factoring the air entering the doorway due to winds, and then due to inside-outside temperature, calculating the total air entering the doorway, and then the heat loss, and then coming out, factoring out the cost of operating the air curtain. And that's going to give you your bottom energy savings.
Hey, Jamie, what do you think from just a conceptual thought? Like, where do people get the aha moments on this? I mean, I know there's a calculator, but I'm thinking to myself, it's not really like a cold source because the wind's blowing in. Like, is that maybe where the gap is? Or what do you find when you found people that go, oh man, I'm all about air curtains? What do they say? What do they say to you?
Anybody say to me, I love air curtains, but
Maybe after today.
for instance, when I was younger, my college days, I worked at Joe's Crab. I don't know if you guys are familiar with Joe's Crab. Probably one of the worst seafood restaurants ever invented, but this is how I paid my way through college. There was a door, there was a vestibule. Wintertime, Christmas shoppers, it was busy. There were a couple doors right by that vestibule. And what happened all the time, people were standing in the vestibule, both doors were wide open, air coming in, freezing out these tables by the door. People would sit there for 1 minute and then they'd want to leave because it was so cold. For me, right now, looking back, that would be aha moment. You would have paid, not even in your energy savings, you would have paid for that air curtain just in a month of the revenue they were losing by people not sitting in those seats. So I think the aha moment is when you're sitting in somewhere, whether it's a restaurant, a store, even an airport, and doors are opening and you're freezing cold in there. So I mean, it would just take an air curtain, put it there, and you fixed your problem.
Bugs from me.
Yeah, especially bugs. There's a slide here talking about flies, and they are just. I never realized how disgusting flies were until I actually started researching the benefits of using air curtains for them. I did another, if you go to the next slide, please, Michael. This was just to kind of show you the difference. That was a smaller commercial application. This is a much larger industrial door. I didn't do the 3-page printout, but just to kind of give you the significant energy savings you would see for a larger door if you are heating that space. Drop the inside temperature, 3 hours per day that door might be in use. 3 shifts, 7 days a week, a 16 by 16 dock door. Over a $20,000 annual savings. So very significant energy savings for larger openings. Thank you. Increasing comfort, what I was just talking about. This is a CFD design. We have this capability in-house. So if you ever want to see a certain scenario ran, we can certainly do that for you. What you're seeing on the left is just an open doorway without the air curtain operating. The picture on the right is that same scenario, but you do have the air curtain operating. And again, this is Joe's Crab Shack. People sitting in here, that door's open, nothing protecting it, running right into the tables. They're freezing whenever it's January, February, March. They're not wanting to sit there. People are not going to want to stay inside stores and shop if it's freezing cold. So that right there. Also for employees, I don't think people think about employee satisfaction very often. I think of grocery stores. How much does it take for a poor cashier to wake up in the morning and want to go into work when they know they're going to be freezing cold and they're in a hat and gloves and scarves? If you put an air curtain there, it's going to be much more comfortable, likely to improve employee retention, satisfaction, reduce absenteeism. So not just comfort for customers, but also for employees as well. Sanitation, flies. I will not even read all of these facts. They are so disgusting, but I can tell you, We have a Golden Corral, which is again, probably a very bad buffet, but it's one of my favorite restaurants. I love the broccoli salad. After doing this, every time I go in there, there are flies everywhere and I haven't been able to go back because as you can see here, flies are disgusting. When you're at a restaurant and a fly is on the food, the harmful deposits that it's leaving there, it's disgusting. So you will see a lot of Aire curtains also called fly fans, just simply for the fact that they can keep insects out. One common question I get asked is, can we put Aire curtains on the exterior of a building? The only time that we would recommend doing that is if you're using it for bug control. If you're putting an Aire curtain on the exterior of the building for climate control, you are actually going to do more harm than good. The reason being, it's taking in that outside unconditioned air. When that air hits the floor, it splits. So you're actually going to be pushing some of that unconditioned air inside. So bug control, you can put it outside. I always recommend move it inside. Now you not only have bug control, you also have climate control as well. Here's some pictures of that. A couple of different bug control applications, drive-through windows. We do tons of work with McDonald's, Chick-fil-A. They use them at their drive-throughs, not only for climate control, bug control, but also to keep exhaust fumes from entering the facility. This is a water park in Pittsburgh, PA. They wanted to leave the doors open to attract people to come in. However, they were losing their air condition. Flies were also coming in. So they put an Aire curtain there. Here you can see this is I don't even know, out west somewhere, but it's a grocery store, Aire curtain mount on the outside. This is only stopping bugs. It's not doing anything for climate. Safety is another big application for Aire curtain. Few forms of safety. One, a lot of people will use a heated Aire curtain over an entry door to help protect that threshold. When it's really cold outside, you might have snow and ice buildup, people could slip. So they'll constantly have that heat running whenever the store is open to kind of defrost that area. Also, a lot of people will say, oh, we don't want to use an Aire curtain, we use those plastic strips, which I get it. They're I shouldn't say very inexpensive, but they're more cost effective initially. However, I've been into Costco's where they had like a beer cave and they use those plastic strips. And I went into two. The one they had actually cut the plastic strips off so people could just walk under, and the other they had them tied off. So put an Aire curtain up front. It's gonna last longer. It's gonna work much better. It's safer. Kind of give you a clear obstruction. You're not nothing blocking the view from one side to the other. Over here, you can see the ice buildup. I'm not even gonna get into this, but we have a special line of Aire curtains for coolers and freezers. I know a lot of mechanical engineers, it's a specialized segment if you do cold storage. Completely different presentation, but if you do work on cold storage, we do have a line of Aire curtains specifically for that. This is crazy, and I don't even understand how it works myself, but for the freezer Aire curtains, we actually use a electrically heated Aire curtain on the warm side to prevent ice, condensation, frost from building up inside the freezer. But again, completely different concept than what we push Aire curtains, but it works well. All right, getting into better building design. This is the vestibule exception that I was talking about when I started this job 20 plus years ago. Talking to engineers, oh, we don't need Aire curtains, we use vestibules. And I get it, in concept, they're supposed to serve a purpose, but what happens so often is both of those doors are wide open. So you're creating a tunnel, that unconditioned air is coming in, you're losing conditioned air. So vestibules, they're not very effective. Inefficiency in design, they cost a lot of money to build. At $15,000 and up, also you're losing valuable floor space. We do a lot of work with Walgreens, Rite Aid, where they'll intentionally build their stores just shy of 3,000 square feet, so they do not have to include a vestibule. So they're not ideal. Also, if you have swing doors, you're increasing touch points. Now, viruses and germs are a huge hot topic. So you're increasing touch points, the more doors that you have. Also liability, doors, I didn't realize this, but door closures, closing on people falling, breaking hips, it's a thing. So all of these are kind of an ineffective design for vestibules. So we knew this. There's 3 major Aire curtain manufacturers in the United States. We took this and had a study done, which we first took to IECC. In 2015, there was a code update stating you could use an AMCA certified Aire curtain in place of a vestibule. It must be AMCA certified, and here's some of the criteria. Well, number 6 was the update for 2015. It must meet a minimum velocity of 2 meters per second at the floor. It must be AMCA certified, and it must operate off of a door switch. Now, go to the next one, please. ASHRAE 90.1 passed the standard in 2019. So now it is good to go for IECC as well as ASHRAE 90.1. To make this easy on engineers that want to use this, if you go to most manufacturers' websites, I know we have a tab specifically for vestibule exception. It is going to give you a wide range of air curtains that are good to go for this vestibule exception. My understanding, architects in the past, I didn't even want to talk to an architect. It was instant rejection. They hated us. They hated air curtains. However, it is my understanding that architects dislike vestibules more than they dislike air curtains. So it has opened up a whole new arena for us. So we have air curtains that even architects cannot give a strong objection to. There's some that hide in the ceiling. We have small, low profile units. We can powder coat any color. We can wrap, we can disguise them, we can hide them. So architects are much more interested in hearing about air curtains now that they know that they can replace vestibules and they can be a little bit more concealed and a little bit more aesthetically pleasing, shall we say. Getting into proper selection, some things to think about. We have standard considerations as well as special considerations that you might not normally think about. For the, go to the next one, please. For the standard considerations, and again, most manufacturers have a selection tool on their website, making it very easy. It's going to ask you a few questions. It's going to take you to a link that's going to give you the air curtain that they would recommend along with the specs and the performance data. Things to think about, what's the application? Are you using this for vestibule exception? If so, remember it must be AMPA certified. Is it low profile? Maybe you don't have a lot of space and you need something that's a little bit smaller to fit in a tight space. Is it customer entry? Something for customer entrance is typically going to be quieter than what you might have for other applications because noise is always a key concern for customer applications. Do you need something NSF if you're using it for bug control, food service, insect control, interior building separation? This is kind of interesting. That's the reason we ask that is because if it's separating two interior environments, you're not dealing with any outside prevailing winds. So we can scale back the performance quite a bit if it's interior separation. If it's a 16 by 16 interior door, you're not going to need something nearly as powerful as if it was a 16 by 16 exterior door where winds are coming at that door. Cold storage, we also get into wash down environments as well as hazardous duty. So pretty much any kind of application, there's an air curtain for it. Other standard considerations, door dimensions. If you are calling asking about an air curtain, first thing we're going to ask is what's the width and height. Some people will try to oversize the air curtain, making it wider than the actual opening. You don't need to do that. You just need to make sure you're covering the amount of the doorway or window that opens. Is heat required? If so, what kind of heat? Electric, hot water, steam, indirect, as well as direct gas. One thing I do encourage, if you are specifying a hot water or steam air curtain, check over the submittal of what you're getting. I know a lot of manufacturers will just stock coils. Reason being, it's cheaper. You know, if you buy 200 at a time, you're going to get a much bigger discount. I know personally we made the decision not to do that. Prices might be a little bit higher, but sometimes you might need a 2-row coil to get a performance that matches what the building has. So please always carefully check what you're getting in terms of heat performance. Another question I get asked a lot is when is heat required? If you are dealing with any kind of entryway, anytime there's customer comfort's going to be involved, I always encourage, especially in a climate like this, I would encourage considering some form of heat. Now, if it's a larger industrial door, something like this, and you're already heating a space, sometimes it's hard to justify the added cost of heating that air. This is a case study that we did in our factory. We're located in Greenville, Pennsylvania, so about an hour north of Pittsburgh. We get pretty severe winters. This is our dock door. This is just an unheated industrial air curtain that we have over that door. So it is not blowing any heat. Outside temperature this day was 36.5 degrees. Inside temperature with the door closed was 67.6. We open up that door, let the air curtain run for 2 minutes. After 2 minutes with that air curtain operating, it dropped to 66.7, less than a degree. Redid the test, turned that air curtain off. After 2 minutes without the air curtain operating, it dropped to 42.2 degrees. So they really do a great job at protecting that inside air, even if it's just an ambient air curtain for a large industrial application. Other considerations, aesthetics, you know, is an exposed unit going to work? If not, if we're dealing with architects, they don't want to see it. Are we going to have to do something in ceiling? Always, it's best if you can have that air curtain discharge nozzle as close to the door header as possible for performance. Sometimes that's not an option. So if we are going above the ceiling, you'll see that nozzle is not directly over the opening. So there is a rule of thumb that for every inch you go above the door header, you need to move that air curtain out a half an inch. So let's say this is 12 inches. You would need to move that air curtain nozzle out 6 inches up at the ceiling. Very important for performance. If you try to mount it directly up against the wall, it leaves at an angle, so it's gonna hit that glass transom and bounce right back in, and you've lost the protection over your opening. So if we get a call that an air curtain's not working, typically we would ask for a picture of the install, and something might need to be tweaked with this. Getting into in-ceiling mount, there's 2 different ways to do it. There is what we call the chameleon. It's just a bottom air intake air curtain. Intakes here, discharge there, it sits into the ceiling. It is not designed to fit into like a 2x2 grid. The reason being, those are not centered over the doorway. So the air curtain needs to go over the doorway. So it's not designed to fit up in that ceiling. You can also do a standard exposed unit with a nozzle extension. One is not better than the other. It's just personal preference. We still see a lot of engineers going both ways. Some special considerations, negative air pressure. If you have a severe negative air pressure, I don't care how oversized you make the air curtain, it is not going to stop that air from coming in. It's just not basic laws of physics. What we would recommend in that instance, maybe put a heated air curtain there, so at least you're heating the air at the point of entry, making it comfortable. It's not freezing cold air, but an air curtain is not going to stop a severe negative air pressure. Other special considerations, aesthetics. Do you need a special color? Here you can see the top right corner is Lego yellow. That's in Legoland in New York City. Picture in the center, this is in Orlando. I don't know if you guys ever went to Blue Martini at Aire. I'm sure you haven't, because the girls dress like they're at Hooters and you guys would never venture there. But they had open doorways that they wanted to leave open to go outside. The ceiling was the blue. They wanted to have an air curtain. They wanted to hide the air curtain in the ceiling. So that's custom painted to match their ceiling. Picture on the right, this is a Smithsonian in Washington, D.C. They wanted a brass faceplate. So that's actually brass that we punched out to fit into their ceiling. You can do wraps. I mean, those are just Mylar wraps like they put on race cars. Any designs, people are now like making the air curtain stand out with logos and designs. Other considerations, heat. I talked about hot water coils a little bit before, also electric heat. Sometimes you might need a little bit more heat if it's a really cold environment, so we can put more heat in there. Maybe you don't have a lot of power left, so you need to reduce the kW. That is very easy to do. We can give more or less kW depending on the application. Just getting into controls a little bit. Door switches. 99.9% of the air curtains we ship come with a door switch. Sadly, what is kind of standard in the industry is this roller plunger. It is big, it is bulky. If something's gonna break, it's gonna be this roller arm. Just don't use it. We offer magnetic door switches. So aesthetically more pleasing. And we have industrial grade, we have commercial grade. They're gonna work better. Maybe $50 more, they're low voltage, so we have to put a low voltage transformer in the unit. Just a better overall design. So if you're using a door switch, please, I recommend using a magnetic door switch. Other controls, just getting into pretty much anything you can imagine. There's speed switches. We can give backnet controllers, variable speed thermostats, programmable, anything you can imagine as far as controls for air curtains. Smart Touch. This is something new that we recently introduced. And what this does, it's just a touchpad that can pretty much give you any function. The thing that I really like about this is a lot of people want to use the air curtain as a space heater as well as an air curtain. With this, if it's an electrically heated unit, you can easily switch that back and forth. So in like a space heater function, it would run off of the thermostat and also the door switch. So let's say the temperature in the space drops below the set point, that air curtain will kick on low speed. And if the door should open during that time period, it will crank on to high speed. So nice, gives you a lot of flexibility. You can set the time that the air curtain runs. It's one really nice switch that pretty much does everything you need for the air curtain. Something else that is pretty slick, we just introduced this within the last year. We haven't really promoted it much yet. I don't know why, but I think it makes a lot of sense. This actually came from an engineer that wanted to try this technology. It's wind sensor technology. So we have EC motors that are variable speed. So we can now give you an air curtain and the speed will be dependent upon the wind velocity outside. So the windier it is outside, the higher the speed of the air curtain. If it's a calmer day, the less airflow that's going to come out of that air curtain.
So is there just like a pressure, is there some kind of a pressure thing outside?
There's a little wind sensor tube that would need to go through the wall that would sense that it ties into the air curtain. Yep. Installation, very easy. These can go threaded rod to the ceiling. They can go directly to the wall. Some people get creative using copper colored threaded rod. So just very easy to install. Get to the next slide. We do offer brackets, multiple kinds of brackets. A lot of people will say, oh, we can't fit an air curtain. I say, send me a picture of what you have and we can probably give you some form of bracket to go around that door. Vertical, we can vertically mount air curtains. I always recommend going over the door. Better design, that air is going to hit the floor, it's going to split the floor will actually stop it. If you give a vertical unit and you don't have anything collecting the air, it could disrupt processes on the other side. That being said, it is an option. We can do vertically mounts. You would need to specify that on drawings. We put special supports on the motor mounts to handle the weight of it going sideways. Custom unique applications, things that you might not think of, a little bit out of the box. As I mentioned, we get into corrosive environments, so car washes, food processing facilities with washdown areas, seaboard application. Our standard construction is stainless steel casing. With these, we would give you stainless steel fans and housings. We would give special motors that can handle the water. So there are units that are good to go for washdown corrosive environments. This is kind of slick. So we do a lot of work with Costco. We do their beer caves, we do their entry doors. They were originally using electrically heated units. They wanted to switch to indirect gas fired. This is a standard indirect gas fired unit. You have your air curtain, your transitions, and then your indirect gas heaters. This is what Costco has. They were going with this design, but it's big. They're big and bulky, and it's not a pretty air curtain. It was blocking all of this natural light coming in through the glass transom. So what we did, this is our air curtain. It's a top air intake. So normally you would have a front intake. We switched it to top. We put a 90-degree bend in the transition. We were able to raise it up so we could now mount the indirect gas heater and the transition up at the ceiling. So you still have the benefits. It's just kind of a different configuration. Revolving doors. This is a top air intake, air curtains electrically heated. This is a medical facility or hospital. That air was getting trapped in the pockets, going into the lobby area, freezing it out. So it wasn't stopping it, it was just kind of heating it, acting as a space heater. Grow facilities, oh my gosh, these are huge now. Not just for climate control, bug control, but odor abatement. We're working with a company that they do nothing but sell odor abatement equipment for grow facilities. So they will actually use the air curtain on the outside. I guess I misspoke earlier. You can put air curtains on the outside for odor because they're trying to protect the outside. They have to have odor plans in place before they can even get permits to build or do any processes. So they have their equipment inside and then they use the air curtain on the exterior of the building to kind of act as a seal. So they're sealing it so no smells are coming out through that door. And it's the mixing box. This is a hospital in Pittsburgh. They had a parking garage, a big long hallway leading into an atrium. Freezing cold air was coming in through the winter. They could not heat it up. So they wanted to use an air curtain as a mixing box. This is a 12, I believe it's a 12-foot wide unit. This would normally have 40 kW, which would give you about a 30-degree temperature rise. They said, put as much heat in there as you can physically fit. We were able to double it. So we put 80 kW in there, giving a 60-degree temperature rise. So that cold air was coming through. The air curtain was acting as a mixing box. By the time it hit the atrium, it was now warm air. We normally don't stage heat. This time we did with something that large. Just quickly talking a little bit about powered air. As I mentioned, noise is one of the biggest complaints we get when talking about air curtains. People imagine these loud jet engines that blow people's hair all around. What most manufacturers do is they take their blowers and they point them directly out of the nozzle. So imagine you have a 4-inch blower shooting air out of a 2-inch nozzle. It's creating a lot of turbulence, also dead spots, and a lot of noise. So I encourage people at trade shows, run your hand under our competitor's discharge. You're gonna feel a blast of air, nothing, and then a blast of air. What we do, it's a really simple concept. We just shift the blowers to the back of the air curtain, creates a plenum effect. The air pressurizes. When it's released, it's complete coverage. It is also a lot quieter. So there's an outlet velocity uniformity. I always encourage something like that on your specifications, just so you know, there's some people that this might be 50% uniformity, which tells you there's a lot of dead spots. Try and set a certain criteria just to know that the air curtain you're designing is doing what you want it to.
As long as the bugs only come in the bottom.
You're right. But then they can walk through if they're too low, yeah. That being said, some other advantages, everything is fully assembled and pre-wired before we ship it. I know a lot of air curtain manufacturers, it's kind of, you have to build it in the field. You'll get the casing, you'll get the motor plate, the panel. It's not pre-wired. You have to do that in the field, which is adding a ton to your construction cost. Everything's fully manufactured in Greenville, PA, shipped from there. So we do have Revit files available on our website. And I think 1 minute over.
Oh, great job.
Be correct. So thank you. Everybody stayed awake. I really appreciate that. Thank you so much. Any questions?
I think you use a tangential blower, don't you? Is that the difference between powered air, burner, Mars?
We use in the low profile, we use a tangential, like our low profile, our standard commercial case is the centrifugal.
Okay,
We have that low profile where they're tangential, just for spacing constraints is what we have in there.
I've looked at industrial facilities, and the common answer is, well, you know, there's 20 dock doors. They're like, we're not gonna put 20-year curtains in. And the truck is always backed up all the way up to the door. Have you seen different, and have you bumped into it where you had a good argument against that? Because I know they don't always put the truck all the way up to the door. People are walking, whatever.
So typically what we would encourage is, usually there's a couple doors that are used most frequently. Try those, see if there's a difference. And then they do realize the difference, and then they're more likely to spend for the rest.
That's great. All right.
Well, thank you.
Any chat questions? No. Okay, how about a nice hand for Jamie? Thanks, Jamie. All right.
Nice job, thank you.
All right, and our last speaker of the day, some friends of ours from Kalamazoo, Michigan, making a quick trip in. Airflow sold lots and lots. It seems like we don't do very many, like, yeah, me too, makeup units. It's a lot of what we do is specialized industrial, you know, very specific to this market. Some very large, some very customized. So in particular, AbsolutAire is very much yeah, we can do that. We can do that. So they have a unique presentation here. Are you leading with it or are you ending off?
We're gonna grand finale.
You know, okay, so I encourage you guys to stick around the end to see what this, it's like Venus flytrap kind of an apparatus. Stick around for the end so you can see what this is. So we've got about 45 minutes left. We're going to talk about direct fired makeup air. Are you guys ready to roll? Yeah. All right. Take it away. All right.
Thank you, everybody, for being here today. My name is Brandon Gray. I've been with AbsolutAire for a little over 11 years now, working mainly as sales and application engineering. And last year, sales and application engineering. And last year I took on a sales manager role. AbsolutAire, if you don't already know, primarily builds direct fired makeup air equipment. We build a lot of other products, but direct fired makeup air is our bread and butter. And that's kind of what we're going to be talking about today, is applying makeup air into your spaces. That next one. First thing I want to say is we're a firm believer that exhaust air and makeup air go hand in hand. We're not an anti-exhaust company. Without exhaust air, there'd be no makeup air, and I'd be without a job. So some of the best building designs utilize both exhaust air and makeup air. So that's what we're going to be talking about today, is applying makeup air systems to your buildings. We're going to be looking at the negative impacts of negative pressure spaces, the positive impacts of positive pressure spaces, and also some design recommendations to optimize your efficiencies, such as things like dynamic pressure controls, direct gas fired heat, management control systems, and also fan selections, specifically fan types. So as we all know, there are hundreds of processes out there that all require some type of capture exhaust system, whether it's welding, painting, dipping, grinding. All these processes require some type of capture exhaust. And without the proper makeup air that's applied to these systems, what that's doing is creating that negative pressure in that space. If you don't have the proper makeup air to account for that negative pressure, you can have a lot of problems. For starters, obviously that exhaust system that someone paid a lot of money for to put in that space can't function as efficiently as it should, because what's happening is you're essentially starving that exhaust system of the air that it needs to do its job. Think of, like you'll see in a minute, trying to pull smoke out of a sealed container. You can't pull the smoke out unless you poke holes inside of the side of the box. The same thing is happening with your buildings, except rather than holes in the side of the box, your air is being pulled in from thousands of infiltration openings throughout the building. Wall openings around doors, windows, so on and so forth. So what that's doing is creating that negative pressure in that space and pulling all that air in. What happens is you're pulling dirty air into that space, which isn't good. You're creating drafts and cold spots in that space. That can lead to employee discomfort and productivity, reduced productivity. Things like naturally vented appliances like furnaces and unit heaters, boilers, those types of things. Now that negative space is not allowing, it can cause backdrafting on those appliances, which can cause carbon monoxide exposure if it's bad enough. You've got poor air distribution in the space. We also, things like exterior doors become difficult to open, which doesn't seem like that big of a deal maybe, but I've heard stories where the space was under such a negative pressure that the employee was going through an exterior door and the door slammed shut so hard on their arm that it broke their arm. So obviously not good for well-being, but also there's downtime and insurance costs associated with that injury. Like I said, you've got poor air distribution and stratification in that space. You can also see some increase in maintenance and operating costs when you have a building that's constantly under a negative pressure.
There doesn't seem to be a real requirement like, okay, so this is my building, and if I put a process in the building that requires exhaust, I can just put it in. I can just put an exhaust fan in wherever.
I mean, yeah, as long
There
as
is no code, like I need an inspection to change out my air conditioner to a heat pump.
I agree. I don't understand why that is.
Yeah.
And the solutions, people kind of find these solutions on their own, and usually it's just a matter of put a louver in the wall and that'll help relieve that negative pressure, but that's not the best fix. What is the best fix is applying makeup air to positively pressurize that space. So what is that doing? That's now allowing those exhaust systems that you just put in place to actually breathe and pull that air out of the building like it's supposed to be doing. Not only when you're pressurizing that space, think of like blowing up a balloon. When you blow up a balloon, it expands and pushes all the air outward. You're doing the same thing in a building. You're pushing all that air out in the envelope of that space, and eventually it's pushing that air to the outside of the building because it's at a lower pressure than inside of the building when you're pressurizing it. So that does a number of things. For one, any smoke or odors that didn't get captured by that exhaust system are now getting diffused and pushed to the outside of the building and outside of the envelope. So you're really kind of getting an exhaust system plus a secondary exhaust system by pressurizing that space and pushing that air out. Also, if you're pushing that air outside through the openings of that building, you're also minimizing your infiltration in that space. So you're reducing those cold drafts and those cold spots that are making those employees uncomfortable. And so you'll see an increased productivity because the employees are more comfortable. Also, same concept with blowing up the balloon. Now you're pushing that air outward in all directions. You're getting really good air distribution when you're doing that because you're pushing that air all throughout that space, which is minimizing your stratification. Those naturally vented appliances now can vent properly, so you're minimizing the risk of carbon monoxide exposure. Like I said, you've got.
Can you say a little bit more on that?
Sorry, what?
Naturally vented appliances?
Yeah, sorry, things like unit heaters or furnaces or boilers or something like that, where you don't have a combustion blower that's actually pushing the exhaust out of the building. Answer the question.
Yep.
Also, your minimum ventilation rates for the space, you're basically already achieving that with your makeup air units. So you're whatever the space is actually requires minimum ventilation rates. Rather than putting a little wall fan to bring some fresh air into the space, using a makeup air unit to pressurize that space automatically fixes that problem. Yeah, this was supposed to be a visual for what I was just talking about. I'm used to the button click, sorry about that. But anyway, so yeah, this is just kind of a visual of what's happening here. Basically, you've got your makeup air pushing your air into this space here. You've got a lower pressure on the outside of the building, and actually you've got some interesting concepts here where you've got wind pressure on this side of the building actually creates a lower negative pressure on this side of the building, which helps push this air from inside the building out even more so. So you're actually getting, not only are you pushing the air against that wind pressure there, but you're also pushing it out from this side of the building also. Okay, now some people might say, well, I can put a wall fan, an exhaust fan on the wall over here and a louver over here, and that should fix most of my problems, and it will kind of eventually pull the gunk out of the building. But I guess consider this concept. Do you suck out a birthday candle or do you blow out a birthday candle, right? You go, no, that doesn't work, but you blow out the birthday candle, right? So that is because of this principle here. Basically, if you're looking at the inlet of a wall fan, an exhaust fan on the wall, where you're pulling the air, you're really only impacting the area of that fan by about 1 fan diameter or so, based on the inlet velocity versus where it's at. So say it's 4,000 feet per minute at this inlet here, 10% of that velocity, which would be 400, would be about 1 fan diameter away when you're trying to pull that air. So not very effective, 1 fan diameter in distance when you compare that to the size of the buildings that we're talking about here. So if you consider blowing the air like I just showed you with the birthday candle, rather than 1 fan diameter, you're actually able to impact that area by 30 fan diameters just by blowing that air. So 30 times you're able to move that air 30 times further just by blowing it rather than trying to pull it. That's one of the main reasons why pressurization is so effective in your buildings, by blowing that air into the space rather than just trying to pull it out of the space. So we've talked about how pressurization solves problems. We looked at some of the reasons why it's important. Let's take a look at some of the some good design practices to optimize energy efficiency for your selections. We'll look at things like dynamic pressure controls, direct gas-fired heating, management control systems, and fan selection types like I talked about earlier. Okay, so dynamic pressure controls. Go ahead. What exactly are we talking about there? What kind of pressures are we looking at? Does anybody know like what kind of approximate pressure you're looking at for a space to achieve a positive pressure in the building?
I know for like isolation room control, that's like 0.01 inches, but
Yeah.
it used to be like 0.001 inches.
Yeah, exactly.
Is that ballpark?
Yep. I'm surprised it's not higher in an isolation room actually, just compared to,
I
general.
think in Europe it's 0.1, but you can
Yeah,
move, you can move the wall at 0.1.
That would be extreme, but yeah, usually for the applications we see, usually 0.1 to 0.02 is about the most you'll see. So you're not talking a lot of static pressure. Those negative results from negative pressure spaces are in the same area. You start to see a lot of those problems when you're at the 0.0, 0.02 negative pressure spaces. So 0.01 to 0.02 inches of positive pressure in that space is really all you're trying to do. So how do you do this? How do you achieve this dynamic pressure control? Well, all you're doing is varying the amount of outside air that's being delivered to the space to maintain that optimal 0.01, 0.02 efficiency. When your system changes in the building, say your dock doors open up, your exhaust fans kick on and off, your system's changing, so the makeup air unit needs to react to that change in system type. So that's what this dynamic pressure control does. So it accounts for that. It also accounts for things at the unit itself, like say filters load up or belts loosen up. It also automatically will account for those things. So no matter what's happening in space or at the unit, the system automatically adjusts to maintain that optimum efficiency to achieve those positive pressure results. Okay, so how do you, what are your options for dynamic pressure controls? There's two that we typically see. There's generally two that you look at. The first one would be a modulating outside air and return air unit, which operates at usually a constant air volume. And all you're doing is just modulating these linked outside air and return air dampers to vary the amount of outside air being delivered to the space. The other common option is a 100% outside air unit rather than so you're not recirculating any air back through the unit, and then you're varying the volume, typically done with the VFD. So when do you pick one over the other? That kind of depends on the application you're looking at. Generally speaking, you'll see outside air and return air units being used when you're trying to heat and ventilate a space. That's where we see the majority of those units being used. Think warehouses and distribution centers. Those are probably the most common applications for those types of units. So when your building's sealed up and all your doors are shut, your dampers modulate, your outside air dampers modulate closed, just closed enough to maintain a positive pressure in the space. And all you're really trying to do is overcome the infiltration on the envelope. As your doors open up, you create a really big infiltration opening, so it requires more outside air to pressurize that space. Your outside air dampers modulate open. Same thing when the door is shut. So they're constantly modulating back and forth to maintain that 0.01, 0.02. Some advantages of outside air and return air units. One, you've got a constant air change rate being delivered to the space. So you've got consistent air distribution. You've got really good air distribution and minimal stratification because you're constantly turning that space over at a constant air change rate. Another advantage would be you can go down to as low as 15 to 20% outside air on return air units. Actually, we can go down to 15% outside air. Nobody else can, but 20% is obviously very low. So when you're not burning a bunch of unnecessary fuel to heat, unnecessary outside air that you're bringing into the space. So a lot of energy savings there with an outside air return air unit as far as minimum outside air amounts. Some disadvantages might be the fact that you are running the fan at a constant volume. So you're running it at its maximum air volume and brake horsepower that it was designed for that application. So unfortunately, you're not going to see any benefits of reduced electrical costs because of that. Another disadvantage might be that they're not the best applications for units or spaces that are excessively dirty. If you've got really dirty air that's being circulated back through that unit, your filters can load up quickly. You can actually cause some air balance problems if they load up too much. And you can also have some premature component failures with excessively dirty air, specifically like fan bearings for one of them. Fan bearings in the burners itself can cause some premature failures. So looking at variable volume units, 100% outside air variable volume units. So these are typically going to be used when you have varying exhaust loads in the space. And the units are strictly for being used for makeup air for that exhaust load, and you're not trying to heat and ventilate the space with these makeup air units. That's not all encompassing. That's just kind of a general application guideline that I try to follow. Some obvious pros with variable volume units are the fact that, okay, you've got a unit that's designed for 50,000 CFM, but you can run it down to half of that air volume. Obviously, you're seeing a significant savings because you're running that unit at a lower brake horsepower and a lower electrical load on the unit.
Greg, what do you see? Where do you see the market now? Like, you guys sell
one over the other.
Yeah, or is it even split, or is it? I know drive costs for you guys have come down.
Yeah, so that's a good point. It used to be outside air return air units were probably we still see a lot of outside air return air units, and I'm not sure if that's specifically just because of the applications that we see more of. It'd be like you said, because of the equipment costs, the cost of VFDs dropping. that's one of the disadvantages of those system types is you've got VFD costs, you've got motor protection, you've got VFD climate control, sometimes line reactors. So there is a higher initial cost with those setups. As far as where the market's going,
No, I mean, like last year, do you think you sold more variable volume or more outside air return air? I'm sure there's plenty
Probably-
of just constant volume, 100% outside air too, but leaving
Yeah.
that out.
Yeah. I think we sell as a company probably still see more modulating outside air and return air units, specifically because you can get down to that 20% outside air. Not to say that there isn't, honestly, if I'm being honest, what I might see happening soon is you see both, where you'll see an outside air and return air unit with the VFD. A lot of times that's used in like an unoccupied setting or in a heating season. You might run the unit at a lower air volume in an unoccupied mode and set it up for the minimum amount of outside air. And then if you have an occupancy setting, you can run that unit at a higher air volume to meet that demand. So you might see a hybrid that might be more popular coming down the road. Going off memory, I would say we see more outside air return air units, so. Good deal. So let's quickly touch base on direct fire heating. This is basically the most efficient means of heat that you can provide for our industry, because of every BTU of gas that gets burnt ends up in the heated airstream and goes into space. So overall total efficiency of virtually 100%. 92% thermal efficiency when you account for the water vapor that gets generated during the combustion process, but still extremely high when you compare it to things like conventional unit heaters that are about 78 to 82% efficient, or conventional boilers that are around 80 to 83% efficient. So significantly more efficient when it comes to that. Direct fired burners have very low emissions, which they have to be because you're putting those products of combustion into the airstream rather than venting them. So we'll look at low emissions a little bit. Also, one of the big advantages, you've got a really high burner turn down with your direct fired burners. You're looking at 30 to 1, so you can get really precise temperature control. So you don't have big temperature swings. You're not overheating and then cycling a burner off or whatever it is. So you can achieve really good temperature control with your 30 to 1 burners. And when you compare it to other things like, say, indirect gas fired heat, you've got a lower initial cost because it's a simpler design. There's fewer components. You don't have a large stainless steel heat exchanger and combustion blower that you have special controls. So it's a simpler setup with fewer components, and obviously a lower operating cost because of the higher efficiencies with direct fire technology. Some people might be a little bit timid to use direct fire technology, maybe because they're not quite familiar with it. But it's important to note that there are strict standards in place that mandate the design and operation of these direct fire burners. These standards include ANSI 834, which are the 100% outside air standards for ANSI, and then ANSI 8318, which is the recirculating standards. These standards are set in place to ensure the safe and proper operation of these direct fired burners, and every year, well, I'll get to that in a minute, I guess, but it's important to also note that your international and your national fuel and gas codes also require any direct fired product to be installed that's going to be installed on a building is third party listed to be in compliance with those standards to make sure that they're being applied in a safe manner. Some of those testing agencies include ETL or Intertech, AGA or CSA, and UL. And what will happen is we have it, I think it might be 2 or 3 times a year. I can't remember the exact number, but we'll get a surprise visit from ETL. They'll come in and make sure that we're building our equipment to the standards that it's supposed to be being built to. So
Everybody loves surprises.
ANSI standards. Yeah. Yeah, it's fun to make sure that the police come in and make sure you're doing your job right. But it's important, it's It's an important thing to do, so. We mentioned these are low emissions burners, they're very low emissions burners, but let's put some numbers to it. So the industrial hygienists limit your maximum threshold value of iron monoxide to be at 25 parts per million. Those ANSI standards that I just mentioned, they limit the carbon monoxide rise to a direct fired unit at 5 parts per million. So significantly less than the industrial hygienist limits that they have. But you'll actually see about 3 to 4 parts per million on a direct fired burner. So
This is in the discharge or in this space?
this is rise through the unit.
Okay.
Yeah, so discharge essentially, yes.
So your actual whatever's in the field is a lot lower than that.
Yeah, exactly. So yeah, and also to compare that, so your gas cooktop stoves are allowed to generate up to 800 parts per million carbon monoxide compared to 3 or 4 or 5 parts per million. So and you sit right over your stove and cook
Right.
every other night. So it's that scare of carbon monoxide is more of a misunderstanding. The ANSI also has the same limitations on emissions for nitrogen dioxide, aldehydes, and carbon dioxide. And they also set safety. They also require safety devices to be installed. So things like high temp limit switches that make sure you don't exceed your maximum 160 discharge temperature. Also make sure that you're not firing the burner at an unsafe firing rate. High and low airflow switches are another requirement, which ensures basically it comes down to your emission levels come down to how much air you're moving through that burner. That's the most important part of direct fire technology. So there's high and low airflow switches in the unit that make sure that the proper amount of air is being moved through across that burner at all times to achieve those low emissions. And on recirculating units, your firing rate is actually limited based on how much outside air you're bringing through the unit. So as you reduce the amount of outside air, your allowable firing rate actually gets reduced. There's actually a different way of limiting firing rate. It's also based on a CO2 sensor in the space. So basically, if your CO2 levels are starting to exceed those maximum values, you have to limit your firing rate. Typically, it sets it down into low fire until if you're out of an alarm type of condition. So. Let's talk controls for a minute. So controls are one of the biggest ways you can actually improve your efficiencies of your units. Obviously, your standard analog control setups are very simple and effective, but they're limited with their functionality and information. More commonly, we're seeing a lot of building management BMS terminal strip units, where basically the controls contractor wants to take control over the unit, whether they've got an automation system they're going to tie it to, or they're going to install their own controller. So the nice thing about that is it gives those control contractors a lot of flexibility to set the units up. However, you're also putting that performance optimization in the hands of someone else rather than the equipment manufacturer who might know a little bit more about the proper operation of those units. So you might want to actually consider something like an onboard management control system or a DDC control system provided by a manufacturer. So these are extremely flexible control setups. You can set things like scheduling, occupancy set points, occupied and unoccupied set points, building pressure set points, unit cycling set points, economizer set points. So the list goes on and on of certain things that you can tweak on your controls to optimize that energy efficiency of that unit. You also have tons of information readily available at your fingertips with these systems. So you're constantly logging things like building pressures, building temperatures, outside air, return air damper positions, VFD speeds. All of that information is readily available. So when your facility manager goes and looks at what's actually happening in space, you can say, okay, well, this is a big problem. We have to fix this certain thing, and it might be a controls change, or it might be something more serious like a design change. But at least they have that information available to make those educated guesses. Also things like maintenance logs and alarm logs on the units makes a more convenient experience for the facility managers. You've got another convenient thing is you can control one or multiple units with these setups. So you can have 20 units all throughout a building and have one location where you can control set points, so on and so forth for all of those units rather than just going to each remote station for each unit. And you can also tie it into existing or future building automation systems through network protocols. So really, if you're looking to optimize energy efficiency, the setting up your controls with the onboard management system is really a effective way to do that.
So that's a panel that would be inside the building if you had if you know, a unit mounted on the roof, it wouldn't be out on the roof on the unit. It's actually
Correct.
something that's separate.
Yep,
right?
correct. There's kind of two parts to it. There's usually a main controller that's mounted inside the unit that all the analog pieces are wired to. And then that main controller is set up through a front end controller, which can control one or multiple of those units. That front end controller could be in the form of a desktop computer, your phone actually. We're selling more and more units with Wi-Fi functionality, so you can tap into your unit from anywhere in the United States, anywhere you're on the internet, you can see your control setups.
Okay.
And also there's operation stations also that you can mount to the space if that was what you were looking for.
Okay.
Let's look quickly at efficient fan selections, specifically types. Forward curve fan versus backward inclined fans. Backward inclined airfoil blade fans specifically. So your forward curve fans are going to be at a lower initial cost, which is, you know, usually a good thing. But the problem is they're less efficient and they're louder compared to backward inclined airfoil blades. You're also limited on your CFM ranges with forward curve fans. Typically, it's on a single fan, you can probably get up to about 75,000 CFM. That's kind of pushing the upper limits also. They'll operate well to low to moderate static pressures, although you can run them at a higher pressure. I typically don't go over 3 to 3.5 inches on a forward curve fan because your brake horsepower goes through the roof, your noise goes through the roof. That's usually where I kind of draw the line. You can run them a little bit further, but 3.5 inches where I try to make that cutoff point there. That's also an overloading fan. So as your fan speed remains constant and your static pressure, say, decreases for whatever reason, your brake horsepower will actually increase with forward curve fans. So you're overloading the fan and you have the potential to actually overload that motor. Actually, which is kind of a strange counterintuitive thought because as that static pressure decreases, you're increasing your brake horsepower. So that's one bad thing about the forward curve fan design. Backward inclined airfoil blade fans, although they do have a higher initial cost due to their design and construction, they are more efficient and quieter. You have a much larger CFM range with them, up to 200,000 CFM with a single fan. That's for a single inlet plenum fan, but way higher CFM ranges. But more importantly, static pressures. You can run these fans at a way higher static pressure than your forward curve fans. Think of them like a bulldozer. They push that air versus your forward curve fan is just trying to kind of throw that air almost like a baseball. And these fans are non-overloading, so that same comparison to your CFM, every total static pressure decreases, your brake horsepower stays relatively the same, so you don't have to worry about overamping those motors in those situations. Let's look at a quick example use case here. So say we're trying to move 50,000 CFM at 1.6 inches of total static pressure. My forward
Which isn't much.
not much.
You got a half an inch of
Yeah, and this is
external, you're
this
at
is the-
one
this
point
is the
six.
generous one. 1.6 is pretty low. A 36-inch forward curve fan is going to run at about 38.3 brake horsepower, which is not bad, I guess. If we were to put that at a 2.6 inches, it would be substantially higher. It's just they're not great at higher static pressures. Compare that to a 54-inch airfoil blade fan. You're running it at 21.8 brake horsepower. So 38.3 versus 21.8. If you run the units 40 hours per week, that equates to $3,100 annual cost savings or electrical savings just by using a more efficient fan. Mark, I think you should probably recognize this because I think I laid this out for you a couple weeks ago. So actually the payback for that, I think, was like about a year or so, somewhere around a year. So it's a pretty significant difference in electrical costs, especially when you consider buildings that are 2, 3, 4 times the size of that. So really the forward curve fans, they have a really, they're popular and they have a lot of appeal because of their lower initial cost. But really over the long run, your backward inclined airfoil blade fans are going to be the way to go. And that's where the market is trending these days also. A couple other considerations to make. So positive pressure, we've been talking about a little bit. So pressurizing that space, this is a big one, pressurizing that space as you're blowing that balloon up and you're pushing that air in all directions. It actually allows for a ductless design because you don't really need that supply air ductwork to distribute the air like you would in other situations because you're pushing that air outward throughout the entire space. This reduces your design and construction costs because of that. You don't have to worry about A, paying for the ductwork itself, but B, you don't have to worry about fire suppression systems and lighting and roof truss and all that you have to work around also. So it simplifies the design and cheapens it quite a bit. When we're looking at heating, typically you want to see your discharge temperatures no more than about 30 degrees above your room temperatures. What happens when you exceed that 30-degree differential is a lot of times, even though you're pressurizing that space and you're pushing that air outward, that temperature difference, that hot air is still more buoyant than the room air. So it wants to float upwards and still stratify a little bit. So if you can maintain that 30-degree differential or less, you'll probably see about 0.1 inches of temperature differential per foot of height in your space. Versus if you start to exceed those numbers, I think, Tom, you said it earlier, you'll see typically about a degree per foot of height to that building when you've got.
Usually makeup air systems that we sell have a higher discharge air temperature than 100 degrees, don't they? I mean, that's not typical, is it?
A discharge temperature of 100 degrees?
Yeah.
That's typical.
Is that typical?
Yes.
Okay.
Yeah.
Like I said, that's totally typical.
Yeah. Well, to 100-degree discharge temperature or temperature rise?
No, 100-degree discharge, assuming a 70-degree space.
Okay, yeah, so pretty typical, yeah.
Okay.
Yeah, there are some other systems out there that try to heat spaces using 160-degree discharge temperatures, the max you can do, which can cause stratification issues. So aim for that 30-degree differential, and you'll see a lot less stratification in that space. One other thing in your intermediate seasons, when you're using outdoor air to ventilate and cool the space, you're still pressurizing that space, but it's nice to know that your cool air is actually going to stratify naturally towards the floor level. So something to keep in mind. Jump back to the positive pressure thing real quick. I will say there are some spot cooling applications where you do need to run ductwork. It's not all encompassing. Positive pressure doesn't solve all ductless design systems. There are some applications with cooling that do require ductwork, but we're not talking about cooling today. Let's look at a couple success stories real quick. So this first one, this is a locomotive remanufacturer or repair facility that was using a steam boiler heating system to heat their space. And they've been using that same steam system for years and years and years. On average, they were spending up around $90,000, recently up around $90,000 in the month of January to heat their building. Finally, the owner got tired of paying these absurd heating costs, so they went to contractor to see what kind of recommendations they could do to reduce those costs. Mike, when you get a sec there. So what they recommended is replacing their direct fired heating or their steam heating system with the direct fired heating system in place. I believe it was an AbsolutAire return air circulating unit. So they installed the units, monitored their cost for a year, and their January heating cost went from $90,000 down to $46,000. Just by installing these direct fire makeup air units. So substantial cost savings just by updating their heating system to a more efficient solution. 48% reduction.
It was like just a
Yeah.
makeup air system with steam. Or was it some other heating?
They weren't makeup air steam, they were basically small steam unit heaters.
Oh, space.
Yeah, so I think there were, maybe steam fan coil units, but there were units all through everywhere. Which also is expensive cost when you think about all that steam steam piping that has to be ran everywhere, so. But yeah, as far as heating savings, pretty significant difference there. So that owner was so excited that the next year they went back to the contractor and said, what else can we do to make things a little bit better? So they ended up saying, well, we can replace your analog control systems with the management control system with these units. Then they monitored costs again for that year, and they actually saw an additional 17% reduction in their January heating costs just because they were using the technology to optimize the efficiency available in those units. So yeah, $46,000 down to 38 just by upgrading their controls a little bit to use them a little bit more efficiently. I think that was a 57% overall savings just by going to a more efficient heating system like direct fire units and then using a more sophisticated control system. So another success story is a cold heading or cold forming screw manufacturer facility. This space had about 20,000 CFM of process exhaust in it. And the cold heading process creates a lot of oil mist that ends up in there when you're creating these machine screws. And so that's a problem that they were facing in this building. They had a lot of oil mist there. They had 2,000 CFM of process exhaust. And their contractor on the job kept saying, and their problems weren't still being solved with the oil mist problems still weren't being solved. So the contractors first installed a few general exhaust fans on the building to try to fix the problem. That didn't fix it. They installed more the next year. That still didn't fix it. They ended up with 200,000 CFM of general exhaust to try to fix their problems, plus the 2,000 CFM of process exhaust they already had. So they were at negative 400,000 CFM in that space, which is concerning. So finally, their problems still weren't being fixed. The owner went to a different contractor looking for a solution, and that contractor said, "Okay, you don't have any exhaust. You don't have an exhaust problem. You've got a makeup air problem." So what they recommended is putting 210,000 CFM makeup air units in space, which equated to about 3 air changes per hour for that building, which is pretty typical for most of the applications you're going to see. Is 3 air changes per hour is going to clear your space out pretty effectively. So they not only did they install the makeup air units, but they actually recommended turning the exhaust fans off, the general exhaust fans off, because what those are doing is actually almost you're not allowing those process exhaust systems to actually do their job because you're creating that negative pressure by trying to pull that air out. So basically, let your process exhaust do its job. Give the air that it needs with the makeup air units to do its job. And the problem should resolve itself. Typically, so we ended up with 200,000 CFM of process exhaust, 210,000 CFM of makeup air. Rule of thumb, you'll see anywhere between, this says 10, I think it's actually more like 5 to 15% of additional makeup air compared to your exhaust air is a good rule of thumb to follow. So a couple pictures there. So this was the building before, and I apologize, the quality of the picture is not great. But you can see that there's basically you can't see anything. Is a good way to put it. I don't know how it's gonna slide 2 is gonna show up on the next one here. This is all oil mist in the space that wasn't being cleared. So what happened is they shut the general exhaust fans off. They got the makeup air units installed, get the makeup air units on, and then 20 minutes later went from this to this, which still isn't that great of a quality of a picture. But you can see just in 20 minutes that it clears up that space, and you can actually see these pillars, you can actually see these doorways. Just at 20 minutes at 3 air changes per hour. So it's pretty significant what you can do with just putting makeup air into the space and letting your process exhaust actually do its job. Even without those general exhaust fans that the contractor kept adding and adding. He probably had a nice year that year selling exhaust fans. So yeah, this is just another example of how pressurization can solve problems. So David, all ready?
Yes.
So we got a little demo just to kind of demonstrate the.
Tamara and Mike, can we, you guys can be able to adjust the cameras so you can see.
That's what he showed in his illustration, but I don't know.
For those of you at home, we're just gonna try to adjust the cameras so you can actually see the demo. So just give us a couple of minutes and we'll be there.
Yeah, that's a good question.
Hi, I'm Dave. Just to kind of warm you up to what is happening here. There's two fans that are the exact same CFM, they're computer fans. So they're matched, same manufacturer, same fan. One is an exhaust fan. And it's not that one.
Hold on, Dave.
That's that
Don't go
one.
too quick. We're still working on getting the
Fan on the right
audience
is-
viewers seeing this properly.
We're gonna put the smoke production right under the exhaust fan, give it a fair chance to pull all that smoke right out of this is the building, by the way. We're simulating the building. Good, right? Okay, how long? This is a welding shop. Or it can be, or a foundry or. How's that? Yeah, this is it's going to be exhaust only. In a foundry or welding shop. We're going to use an exhaust fan. Now you can see cracks in the building fabric like there is in any building, right? There's older buildings are worse than new. Where air is coming in and it's kind of making a beeline right for that exhaust fan. See it coming in this side as well? And there's smoke coming out of the exhaust fan. You can see the height of the plume. Okay, let's try make up your own. Okay, now you can see actually for this experiment, more smoke coming out of the exhaust fan with it off than is coming out on or coming out with it on. And there's also smoke coming out of source of cracks in the building fabric. Might be a leaky door seal or could be a where the roof meets the walls. We're going to put more smoke in the building. It's clearing out pretty quickly. What's that? Yes, you got to break it up. It's now 2 more carefully measured cups with the exact same amount of hot water. That's why we're not timing it, because it's not a fair comparison. Look, it's small. Okay, I'm gonna make the smoke again. We're gonna do a push pull, which is a very good design. Gonna help that exhaust fan to work a little bit. We're not any exhaust, just exhaust without makeup air doesn't work so well. Okay, now look at the height of the plume. And there's still smoke coming out of cracks in the building fabric from pressurization, slightly pressurized. And it will clear out space really expeditiously, especially where the supply fan is coming down into the building. That's where it really does the best job.
But goes quickly.
It clears it up quickly.
So pressurization solves problems. Final thoughts, keep it hot. Hint of positive pressure, outstanding but overlooked efficiency of direct fire technology, and turn off and terminate those general exhaust fans, those unnecessary general exhaust fans. So keep it hot. Questions?
Perfect.
All right, how about a nice hand for Frank and Dave and AbsolutAire? Very much. That concludes our presentation for today. Give us maybe a week or a week and a half. We'll get your PDH credits for everybody here and everybody remotely. If you have any questions, you can email events@airflowreps.com, or you can email me. And we'll make the slides available, the recording available, PDH questions and answers available. And thanks, and we'll see you next month for our next class.
Next